Okay. A very good evening, all. So, in the yesterday's session, we discussed about the expressions for input power factor when the source current is a square wave and the source current is a quasi square wave, right? Yes. So, let us first discuss this numerical, and after that, we will discussing about the effect of source inductance on the performance of rectifier, and after that we'll discuss some numericals related to the source inductance, and next we'll be proceeding towards the three-phase rectifier. Okay, so before that there is one announcement. Tomorrow from 6:30 to 9:30, there morning 6:30 to 9:30, there will be a session of power electronics. Okay, no T&D session tomorrow. Tomorrow morning 6:30 to 9:30, there will be a session of power electronics. And also in the evening, as per regular schedule, 5 to 9, we'll be having a power electronics again, right? So tomorrow morning and evening, right, we'll be having a power electronics session. So let us discuss this numerical. A single phase full bridge converter is used to regulate DC output voltage. The RMS value of AC input is 230 volt. Okay, so we're having a single phase full bridge converter. RMS value of AC input is 230 volt. That is Vs is given. It is a 230 volt. Frequency is a 50 hertz. The firing angle is a 45 degree. That is alpha is given. So that the load current is a 5 ampere. So here load current is actually constant, I0. It is a 5 ampere. Calculate the DC output voltage. That is a V0 average we need to find. Active and reactive power input with and without freewheeling diode. Okay, means we need to consider full bridge converter with RL load. First case we are going to find the answers for with freewheeling diode. Second case without freewheeling diode, or vice versa. Okay, or vice versa. Next, repeat the question with alpha equal to 60 degree and compare results as an exercise. Okay, so you can find the answer for the third bit. Okay, that will be the homework for you. Okay, for the first bit, that is for alpha equal to 45 degree, how to simplify, that we will discuss here. And for alpha equal to 60 degree, that will be the homework for you. Okay, so yes, so let us first of all note the data. Yes, we are having a single phase full bridge converter. Single phase full bridge converter. The RMS value of AC input is, that is Vs, is equal to 230 volt, 50 hertz. Firing angle alpha equal to 45 degree, right? And load current I0 is equal to capital I0 is equal to 5 ampere. They have given. Calculate DC output voltage. Yes, how to find the DC output voltage? Let us first put the heading. Let us first find for without freewheeling diode, and after that we will find for with freewheeling diode. Okay, so let me write first one, without freewheeling diode. Yes, if the load is RL load, I0 constant means load current is a, or the load is highly inductive. Yes or no? If RL load and I0 constant means it is a highly inductive load, right? So the conduction will be continuous conduction. And suppose if we are having a without freewheeling diode, then how to find the V0 RMS? Yes, can anyone? V0 RMS is equal to, sorry, V0 average, na? DC output voltage. DC output voltage means average value only, right? V0 average. How to find the V0 average? 1 by pi integration from alpha to pi plus alpha, na? Without freewheeling diode means what? From alpha to pi, V0 is same as that of the supply voltage, that is positive. Pi to pi plus alpha, inductor will release the energy, right? Through thyristor, right? T1 and T2. Means here V0 during pi to pi plus alpha, it will be negative, na? Without freewheeling diode means in the V0, right, you will be getting the negative pulse. Okay, so V0 average is equal to 1 by pi integration from alpha to pi plus alpha. It is a Vm into sine of omega t into d omega t, na? So if you simplify it, we'll be getting it as a 2 Vm by pi into cos alpha, right? 2 Vm by pi into cos alpha. This is the V0 average. Now we are calculating it for 45 degree, right? 45 degree. So yes, let me write it as, which is equal to 2 into what is Vm? 230 into root 2, na? 230 is RMS value. So 230 into root 2, that will be the peak value. Okay. So 2 into 230 root 2 divided by pi into cos of 45 degree, right? Cos of 45 degree. So if you simplify it, okay, so 2 into 230 into root 2 divided by pi into cos of 45, right? So it is a 146.42, na? 146.42 volt. This is for, we are discussing alpha equal to 45 degree, yeah? Alpha equal to 45 degree, right? Next, so this is the V0 average, straightforward. Next one is the active and reactive power input with and without freewheeling diode. Okay, so we are discussing the without freewheeling diode. Okay, and our task is to find the active power input. So how to find the active power input? Yes, we know, right? So active power input, that is second bit, na? Yes, active power input is equal to Vs1 into Is1 into cos of angle between Vs1 and Is1. Yes or no? What is this Vs1, Is1? Whether these are the peak values or RMS values? These are the RMS values, na? So Vs1 RMS into Is1 RMS. Okay. Now, what is the Vs1 RMS? Vs1 RMS is nothing but Vs RMS. That is nothing but Vs RMS. How much? It is a 230 volt. Okay. So let me write it as a Vs1 RMS is equal to 230 volt. Is equal to 230 volt. Now Is1 RMS we need to write. Okay, we need to find the Is1 RMS. Now if you recall, without freewheeling diode case, how is the nature of source current? Come on, how is the waveform of source current? We discussed it. Without freewheeling diode, source current is whether it is a square wave or quasi square wave. Come on, it is a square wave, na? Right? It is a square wave. So we know, na, for square wave, we have yesterday we have written the Fourier series expression. Okay, and from that we are having the Is1 RMS also. What is that Is1 RMS? Yes, we are having it is equal to 2 root 2 into I0, na, divided by pi. Yes or no? Right? It was actually 4 I0 by pi. That was the peak. Divided by root 2 means 2 root 2 I0 by pi. This is for square wave. Square wave means what? Without freewheeling diode. For quasi square wave, it was a different, na? It was like into cos of alpha by 2 was there. Okay. So now from this, can we write it is a 2 root 2 into what is I0? They have given it is a 5 ampere. Right? Divided by pi. So if you check 2 root 2 into 5 by pi. Yes, it is a 4.5 ampere. No? 4.5 ampere. This is the Is1 RMS. Next, what is the angle between Vs1 and Is1? Vs1 is a pure sinusoidal. And for Is1, yes, we have written the expression. Okay. So it was angle of sine of in bracket omega t minus alpha. Na? Yes or no? Right? So here it is like into cos alpha will be there. So therefore, active power input is equal to 230 into 4.5 into cos of angle is 45 degree, right? So if you check, it is equal to 230 into 4.5 into cos 45. 731.85, na? Yes or no? right? Yes, please check. Yes. So actually, if you check the option answer, they have given as 732.11. Why it is different? Because actually we have considered it as 4.5. But if you take this ratio, it is 2 root 2 into 5 divided by pi. Na? So it is 4.50158, right? So due to that, it is a different we are getting. So let me write it as a that full term 4.50158 into this term. So it is 230 into 4.50158 into cos of 45. So it is 732.1 watt. This is the active power input. Right? So we have calculated VS1 RMS. It is straightforward. They have given VS is 230 volt AC. After that, we have written IS1 RMS, right? Because we know now power P is equal to V into I into cosine of angle between V and I, right? So here VS1 IS RMS, IS1 RMS into cos of angle between fundamental voltage and fundamental current, right? So IS1 RMS we have calculated. That this expression we have already derived in the yesterday session, right? So now similarly, can we write the reactive power input? Reactive power input. Same, what will be the change for reactive power input? VS1 RMS into IS1 RMS into sinusoidal of angle between the two, na? Right? So let me write VS1 RMS into IS1 RMS into sine of angle between VS1 and IS1. So you can check it is a 230 into this thing is we have written 4.50158 into sine of angle between the two is sine alpha. Okay, that is a 40. Yes, let me write it as alpha first. So 230 into 4.50158 into sine of 45. Na? So if you check, it is 732.11. Na? It is a volt ampere reactive. It is a volt ampere reactive, right? Reactive power input. This much. Is this clear? Load is RL here because they have said key load current is constant. Actually, after decimal, we should consider the 2 points, right? Yeah. Right. Right. Okay. So 732.11 VAR. Next, similarly, can we find for the second bit with the freewheeling diode? With the freewheeling diode, right? We are having the with freewheeling diode also. So we have written here without freewheeling diode. Let me write it as a with the freewheeling diode. Yes, Vishnu, do you want to?
Sir, yes, sir. Just one question, sir. 3F,
Yes.
sir. In 3F, the yesterday we derived that power factor as 0.9 cos alpha.
Yes.
So that 0.9 we approximated as 1 and we have just left it, or
0.9.
that 0.9. So actually the power factor, input power factor cos phi s is 0.9 cos alpha, right, sir?
Yes.
But in the expression we have just used cos alpha.
Okay, here you are saying.
Yes, sir. So that's what I wanted us. That 0.9 was rounded off.
Thing is that 0.9 now.
About.
That 0.9 is already included here. You can check 2 root 2 by pi. That is a 0.9 only.
Oh, okay, sir. Okay, sir.
Right?
Okay, sir.
Okay. With the freewheeling diode. So again the same thing, Vs is given. So Vs1 is equal to 230 volt. Vs1 RMS, right? This one is. What is IS1 RMS? Recall. Now with the freewheeling diode means what is the nature of the source current? It is a square wave or quasi square wave? Come on, speak out. Quasi square wave, right? It is a quasi square wave. Okay. So here with freewheeling diode means the source current is a quasi square wave. And we are discussing it for alpha equal to 45 degree now again. Right? Alpha equal to 45 degree. So recall the yesterday's expression, whatever we derived. Okay. So in that we have written IS1 RMS is same 2 root 2 into I0 divided by pi na into the term was there. That is the cos of alpha by 2. Yes or no? Cos of alpha by 2. Right? This is your IS1 RMS. Check the yesterday's expression. Okay. So it is equal to 2 root 2 into phi divided by pi into cos of alpha is 45 degree divided by 2. So if you check, it is equal to 2 root 2 into phi by pi into cos of 45 by 2 means it is a 22.5. It is 4.1589, right? 4.1589 ampere. This is the IS1 RMS. Now how to find the power, real power, that is active power and a reactive power? Yes. So first bit, active power. This is actually second bit. First bit is your V0 average. Okay. We'll discuss it at the end. So active power input is equal to Vs1 RMS into IS1 RMS into cos of angle between these two, na? Vs1 and IS1, right? So if you check, it is equal to 230 into 4.1589 into what is the cos of angle between Vs1 and IS1? It was a alpha by 2, na? Right? So into it is a cos of alpha by 2. So it is 230 into 4.1589 into cos of 45 by 2. So if you check, it is equal to 230 into 4.1589 into cos of 22.5. 883.734 watts, na? This is active power input. Similarly, find the reactive power input. Reactive power input. Yes, same Vs1 RMS into IS1 RMS into sine of, okay, angle between Vs1 and IS1. So it is equal to 230 into 4.1589 into sine of, what is the angle? It is alpha by 2, right? Sine of alpha by 2. So it is equal to 230 into 4.1589 into sine of 2.5. 366.054, right? Volt ampere reactive, right? Volt ampere reactive. This is the reactive power input. And first bit they asked for V0 average. How is the V0 waveform for RL load with the freewheeling diode? alpha to pi, V0 is a Vs na, pi to pi plus alpha, it was 0 na, right? So it is like 1 by pi integration from alpha to pi Vm into sine of omega t into d omega t, right? So it is equal to Vm by pi into 1 plus cos alpha. So it is 230 into root 2 divided by pi into 1 plus cos of 45 degree. Na? So if you check, it is yes 176.747. 176.747 volt. Okay, you can check the average value with the freewheeling diode is greater than that of whatever the average value we calculated for without freewheeling diode. Okay, without freewheeling diode it was like 146 something, here it is 176. Because why this is greater? Because in the RL load with the freewheeling diode, okay, the V0 negative pulse in the V0 waveform, the negative pulse that is from pi to pi plus alpha, okay, that negative pulse will not be there. So that's why the average value will be, yes, improved. So this is about this for alpha equal to 45 degree. Similarly, for alpha equal to 60 degree, follow the same steps, right? And you will be getting the answer. Okay, so next. Yes. So now we are going to discuss the effect of source inductance. Okay, effect of source inductance. Source inductance on performance of single phase fully controlled rectifier. So what is the source inductance? Let us first understand, then we'll discuss what is its effect. Okay, so if you check for a rectifier, yes, rectifier is a circuitry which converts input AC to the output DC. Okay, and for a rectifier, actually the input is given through the transformer. And if you recall the equivalent circuit of a transformer, in the transformer we are having a primary side leakage impedance, secondary side leakage impedance. Yes or no? Primary side we are having R1 plus JX1, secondary side we are having R2 plus JX2 na, right? What is that R1? R1 is nothing but your primary winding resistance of the transformer. X1 is nothing but the leakage reactance, okay, that is associated with your leakage flux of the transformer. Similarly, at the secondary side also we are having the R2 plus JX2, that is the leakage impedance at the secondary side. Okay, so as between the supply and the rectifier we are having a transformer present. Okay, in real life, yes, our rectifiers are generally feed with or through the transformer. So here, as the in the transformer, yes, there is a leakage impedance, and in the leakage impedance we are having the two components, one is the resistance and second one is the reactance. Okay, now you can check what is the value of that resistance. Comparative value of resistance is very less. Okay, so more or less your leakage impedance means what? It is a reactive component only, right? So that's why here in this circuit, whatever the circuit operation till now we discussed, in that case we have neglected the source inductance. But now here we are going to discuss what is the effect of that source inductance, okay, on the performance of this single phase fully controlled rectifier. Okay, and the effect of that source inductance will be observed, okay, will be observed or will be more when the load is a RL load and a highly inductive load, when the load is a highly inductive load. So that's why here we are going to consider the single phase fully controlled bridge rectifier with a highly inductive load, right? Important thing, first thing is what is the source inductance? The source inductance is nothing but the inductive reactance of a transformer. Are you getting the point, right? So here inductive reactance is there. So that's why here we need to consider actually the inductance of that transformer, leakage inductance we can say. Okay. So, and what is the effect of that inductance on this rectifier, that we are going to discuss here. We know the inductance causes the opposition to the change in the current, right? With that same tendency of the inductor, okay, we are going to discuss this concept, right? So let us consider single phase fully controlled rectifier with a highly inductive load, right? With a highly inductive load. So let me draw the circuit diagram. Suppose load is highly inductive. Suppose the inductance is present here. This LS is nothing but the source inductance, right? Actually, this is the inductance of a transformer, right? So T1, T2, T3, T4. Let me indicate this current is IT1, IT2, IT3, and IT4. This is a IS, here it is a I0 and a V0, right? Now, so let us first recall the waveforms, okay, of this single phase fully controlled bridge rectifier with a highly inductive load without LS. I am saying without LS. First of all, we are going to draw the waveform, okay, and after that we will discuss what will happen, okay, if the LS is present, right? So let us first recall the waveforms without LS. I am saying, okay, so without LS, without LS. So our waveforms, yes, okay. So here, first thing is 0 omega t, your V0 waveform. If you check here V0 waveform, it is like this now, from alpha to pi, pi to pi plus alpha, pi plus alpha to 2 pi. Okay, so waveform is from 0 to alpha, it is a negative. After that, it is a positive type of thing. And next again negative, and again the same positive. Yes or no? This waveform we already discussed, right? Alpha, pi, pi plus alpha, 2 pi, right? This is your V0. How is the waveform of I0? Yes, I0 is a constant current because load is highly inductive. This is the waveform of I0. How is the waveform of IS? If you check in this case, the waveform of IS, it is like a RL load without freewheeling diode, na? So yes, IS is a square wave, right? It is a square wave. So waveform is like this. This is we are discussing without a freewheeling diode, right? Sorry, without LS. Next, how is the waveform of IT1, IT2, IT3, and IT4? Yes, can anyone? Suppose I want to draw the waveform of IT1, IT2. I want to draw the waveform of IT1, IT2. Let me draw here IT1 and IT2. Whether the waveform of IT1, IT2 will be same or different, you can check the circuitry. Whether the waveform of current flowing through thyristor T1 and thyristor T2, that will be same or different. You can check when T1, T2 conducts, current will flow like this, na? First of all, remove this LS. we are discussing the waveforms without alias first. Okay, so IT1, IT2 will be same na. IT1, IT2 will be same, right? So yes, during which interval T1, T2 are in a conduction mode? T1, T2 are in a conduction mode only from alpha to just a minute. This waveform should be not like this. Yes or no? Please check the IS waveform. This is like this, na? We're having this type of waveform. I'm sorry. Yes or no? 2 pi to 2 pi plus alpha, and again it is like this. Okay. So this instant is like 2 pi plus alpha. From alpha to pi plus alpha, T1, T2 are in a conduction mode, na? Right? So here we are having the IS like this, I0, and here it is a minus I0. Please correct it. Next, so during alpha to pi plus alpha, T1 and T2 are in a conduction mode, na? Right? So therefore, IT1, IT2 will be non-zero, and that will be equal to same as that of your load current, and which is equal to source current again. You can check when T1, T2 conducts, suppose the source inductance is not present. Suppose let us consider the source inductance is not present. So when T1, T2 conducts, current is flowing from Vs, T1, load, T2, and again back to the Vs, right? So IT1, IT2 both are same, which is equal to I0 only, na? Right? So therefore, I0 here you can check, it is a positive always. So IT1, IT2 waveform will be like this. 0 to alpha, it is a 0. Alpha to pi plus alpha, it is the same as that of the load current I0. At pi plus alpha, it will be 0 na, because next thyristor pair will start conduction. Okay, and next you can check here. Yes, this type of waveform at 2 pi plus alpha, again the same repeats. Okay, this is the IT1, IT2 waveform. Similarly, can we draw the waveform of IT3, IT4? IT3, IT4 waveform, can we draw? Yes, let me draw here. We are discussing without LS only. Without LS. How is the waveform of IT3, IT4? Thyristor T3 and T4 are in a conduction mode only from omega t is equal to pi plus alpha to 2 pi plus alpha. Okay, so it is alpha, pi plus alpha, 2 pi plus alpha, right? 2 pi plus alpha. So the waveform is from pi plus alpha to 2 pi plus alpha. IT3, IT4 are positive. Please be careful. When T3, T4 conducts, na, pi plus alpha means supply voltage is minus here plus here. Okay. So current is flowing like Vs, T3, load, T4, and again back to the Vs. In this loop, current will be flowing. So your IT3, IT4 are positive. I0 is also positive, but your source current is negative, na? Right? Same thing we discussed. So pi plus alpha to 2 pi, you can check. IT3, IT4 is equal to I0. That is a positive. But during the same interval, if you check IS, during the same interval IS, pi plus alpha, 2 pi plus alpha, it is a negative. IS is negative, but IT3, IT4 are positive. Okay, so it is a positive. Next, alpha to pi, what will happen? It is a 0 because T1, T2 are in a conduction mode. Okay. Next, whatever the waveform we're having from 2 pi to 2 pi plus alpha, same will appear during 0 to alpha also, na? So the waveform will be like this. During 0 to alpha also, it is a positive. During 0 to alpha also, it is a positive, right? So this is again I0. Okay, so these are the waveforms of single phase fully controlled bridge converter or rectifier without the effect of LS. Without the effect of LS. Now you can check here. If the source inductance is not present, then what we are observing here, IS is changing from minus I0 to the plus I0, na? Within a 0 time or sudden change is there. Similarly, you can check at pi plus alpha, IS is changing from I0 to the minus I0. In a 0 time means a sudden change is there. Also here at 2 pi plus alpha also, IS is changing from minus I0 to the plus I0, means the sudden change is present here. In the source current, I am saying, in the source current, sudden change is present. This is true when LS is not there, that is the source inductance is not there. But Suppose if the source inductor is present, if the source inductor is present or a source inductance is present, whether our source inductance will allow this sudden change at alpha, at pi plus alpha, at 2 pi plus alpha, whether our source inductor will allow the sudden change in current? No, because the basic tendency of the inductor is to oppose the change in the current. Na? Yes or no? Are you getting the point? This is very important, right? Because you can check without LS, the IS is changing suddenly. At alpha, it is changing suddenly from minus I0 to the plus I0. At pi plus alpha, it is changing suddenly from plus I0 to the minus I0. At 2 pi plus alpha also, it is suddenly changing from minus I0 to the plus I0. This is true only when, or this is possible only when your LS is not present, that is the source inductance is not present, right? But if the source inductance is present, then what will happen? But if the source inductance is present, then what will happen? Our says inductor, source inductance means LS will be present here, and that LS will not allow, the sudden change in the current through it. So which current is flowing through the LS? IS is flowing through the LS, na? And here you can check due to this LS, whether our IS will suddenly change at alpha, at pi plus alpha, at 2 pi plus alpha? No. So there will be a slow change. Okay, means IS will be slowly changing from minus I0 to the plus I0 at alpha, as well as at pi plus alpha, as well as at 2 pi plus alpha. Okay, so now let me draw first the IS waveform. Let me draw first the IS waveform with LS. Okay, IS waveform with LS. So let us put the heading with the LS. Means when the source inductance is present, then what will happen? IS here it is omega t 0. We are having a alpha. This is a pi plus alpha, 2 pi, and suppose this is a 2 pi plus alpha. So you can check IS waveform. Definitely between 0 to alpha, it will be as it is. Okay, between 0 to alpha, it is as it is for continuous cycle. Okay, so it is a negative only. At alpha, without LS, there is a sudden change, but due to the LS, this sudden change is not possible. The meaning is our IS will change slowly from this minus I0 to the plus I0. Slowly change means what? It is like this. IS will change slowly from minus I0 to the plus I0, right? Minus I0 to the plus I0. After that, it will continue till pi plus alpha. After that, it will continue till pi plus alpha. At pi plus alpha, you can check there is a sudden decrease, na? Plus I0 to the minus I0. Again, due to the LS, that sudden decrease is not possible. So the thing is, our LS or the IS will decrease slowly because our LS is opposing. This will continue till 2 pi plus alpha as it is. Okay. And at 2 pi plus alpha, again, what is happening? Again, the slow change is there. So it is a omega t. And at 2 pi plus alpha, again, the IS will increase from minus I0 to the plus I0, but it is a slowly increasing. So this is the main difference between the IS waveform. Here it is a slowly changing, slowly increasing, you can say, slowly decreasing, slowly increasing, and again the next slowly decreasing. Whereas in the previous case, it was a sudden increase, sudden decrease, sudden increase, sudden decrease. Okay. Now, what is the effect of this? What is the effect of this slowly changing, slowly decreasing, slowly increasing, slowly decreasing on thyristor currents? Let us discuss. Okay, on thyristor currents, let us discuss. So if you check if IS is changing like this, if IS is changing like this, okay, so how will the IT1, IT2 and IT3, IT4 waveforms? Let us discuss. IT1, IT2, omega t 0, and here it is IT3, IT4. This is a alpha. Okay. Yes. Now you can check when T1, T2 conducts, when T1, T2 conducts. At that time, it is like a IT1 is equal to IT2 is equal to IS, na? Yes or no? When T1, T2 are in a on state, IS is a positive. Okay. So IS is equal to IT1 is equal to IT2 is equal to I0, na? We are having, right? So I0 is a constant current, right? So let me write, when T1, T2 conducts, when T1 and T2 conducts, at that time your IS is a positive actually. IS is equal to IT1 is equal to IT2 is equal to I0. When T3, T4 conducts, when T3 and T4 conducts, at that time, yes, when T3, T4 are in on state, at that time, what is IS, positive or negative? IS is a negative, na? Right? So can I write it as minus IS is equal to IT3 is equal to IT4 is equal to I0, right? Means the meaning is, please try to understand. IT3, IT4 are positive because you can check T3, T4 are in conduction mode from alpha, na? So it is like current will be flowing like this. Okay, current will be flowing like this here. Okay, so in this branch, actually the current is in downward direction. So source current is negative, but IT3, IT4 are positive. I0 is also positive. Okay, so that's what it is. Minus IS is equal to IT3 is equal to IT4 is equal to I0. Now we are having IS is equal to IT1, IT2, which is equal to I0, and minus IS is equal to IT3, IT4 is equal to I0. Means there is a relation between source current and thyristor current. Source current and thyristor current. Now suppose for the very first cycle at alpha, suppose for the very first cycle at omega t is equal to alpha, means before that cycle it is like energy stored by the source inductor is zero. Energy stored by the source inductor is zero. At alpha, when we apply the gate pulse to thyristor T1, T2, at the alpha, when we apply the gate pulse to thyristor T1, T2, whether the current flowing through thyristor T1, T2 will increase suddenly? No, current will not increase suddenly because of this LS, na? At alpha, when I apply the gate pulse to T1, T2, it is like current will flow from VS, LS, T1, load, T2, and again back to the VS, right? At alpha means this polarity will be plus here, and here it is a minus. So due to this LS, as IS is also slowly changing, and therefore our thyristor currents IT1, IT2 are also slowly changing. Those will be slowly changing. Now important thing here you can check, without LS it is also slowly, it was also IS was it's increasing suddenly, decreasing suddenly, increasing suddenly, decreasing suddenly. IT1, IT2 were suddenly increasing, suddenly decreasing. You can check IT3, IT4, suddenly decrease, sudden increase, sudden decrease. This is without LS. But with LS, this is not possible. With LS, this is not possible. So what will happen? At omega t is equal to alpha, at omega t is equal to alpha, when we apply the gate pulse to thyristor T1, T2, na? So from alpha, or at omega t is equal to alpha, okay, it is like IT1, IT2 will not increase suddenly, it will start increasing slowly. Why? Because of LS. So IT1, IT2 will increase slowly. After that, it reaches the final value, that is the I0. Without LS, it is like at pi plus alpha. Without LS, it is like at pi plus alpha. IT1 was decreasing suddenly, na? But IT1, IT2 are again flowing, completing their path through the source current only, through the LS only, right? So that's why what will happen, our IT1, IT2, okay, will not decrease suddenly, they will decrease slowly. And again, it will be 0 here. And next at 2 pi plus alpha, again the slowly increasing like this. So this is your I0. This is the minus I0. This is also I0. Now what about the IT3, IT4? You can check IT3, IT4. Between 0 to alpha, this is alpha, na? This is alpha. This is like pi plus alpha. Okay. This is like a 2 pi plus alpha. So you can check between 0 to alpha in the continuous cycle. In the continuous cycle between 0 to alpha, yes. What about the thyristor T3, T4? You can check here without LS first. Yes, 0 at alpha it was suddenly decreasing, na? But whether the sudden decrease is possible due to the LS? No, because your IT3, IT4 are also flowing through the LS, na? Are also flowing through the LS, right? And unless and until they circulate through the LS, they will not complete the closed loop. They will not complete the path. Okay. So here your current will be decreasing at alpha slowly from I0 to 0. After that, it is again 0 here. At this instant, okay, this is at pi plus alpha. At pi plus alpha, we are triggering T3, T4 now. So current will not suddenly increase. It will increase slowly, right? It will increase slowly, right? From 0 to I0. And again, it will be having a constant current till 2 pi plus alpha. At 2 pi plus alpha, again, it will be decreasing slowly. So you can check, this is IT3, IT4 waveform. This is your I0. This is your I0. Our thyristor, our switches allows current in only forward direction. Na? Thyristor is a unidirectional switch. We have discussed it in the first chapter. Okay. So switch current is always positive. Source current will be positive or negative. Now you can check here. Now you can check here. Yes. In this case, if you check, we are having the relation like IT1 is equal to IT2 is equal to IS. Okay. When IT1, IT2 are positive, IT1, IT2 are positive, then IS is also positive. So you can check here. IT1 and IT2 are positive, IS is positive. When IT3, IT4 are positive, IS is negative. Na? IT3, IT4 positive, IS is negative. So when IT3, IT4 are positive, your IS is negative. So actually what is happening during this interval from this point to this point or from this point to this point? What is happening in the circuit? What is happening in the circuit? You can check. Here IS is changing slowly from minus I0 to the plus I0. Thyristor T1, T2 current is also changing slowly from 0 to the I0. Thyristor T3 current is also changing from I0 to the 0 ampere. I0 to the 0 ampere. So during this interval from this point to this point, can we say that T1, T2 are also conducting, T3, T4 are also conducting? Because IT1, IT2 is also non-zero. At the same time, IT3, IT4 is also non-zero. The meaning is all the four thyristors will be in a conduction mode. Why all the four thyristors are in a conduction mode during this interval? Because of the LS, because of the source inductance. You can check here. Thyristor current will not change suddenly from non-zero value to the zero value or zero value to the non-zero value, because if the thyristor, because thyristor IT1, IT2 is current is flowing through the LS only now. So whether our LS will allow the sudden change in the current through the thyristors? No. Is this clear? Right? So that's why here you can check the waveform of IT1 will be like this, IT3 will be like this. Okay. So the meaning is this interval is generally, yes, known as your commutation interval, or it is known as the commutation angle or a overlap angle. Mu is nothing but the overlap angle. Okay. So let me write here. Mu is the overlap angle. What it indicates? During this interval, during this angle mu, all the four thyristors are in on state. Are you getting the point? All the four are in on state means what? This is also conducting, this is also conducting, this is also conducting, this is also conducting. Yes or no? Now you can check if all the four thyristors are in a conduction mode. It is like across the source will be having a direct short circuit. Now you can check. This point is here. Again, this is point will be here. Same point will appear here, and here it is across at the negative side, negative terminal. So it is like across the source will be having a direct short circuit. But even though across the source there is a short circuit, this will not cause a circulation of very high current. Why? Because of the inductor. Suppose I am having a 100-volt voltage source. Across that 100-volt voltage source, if I connect a directly short circuit, that is a wire with a very small resistance, if I connect, then what will happen? Very large current will flow, 100 divided by that small resistance of the wire. But suppose if we are having a 100-volt voltage source and in that series we are having an inductor, and again if I connect the short circuit branch, due to that inductor our current will not suddenly increase to a high value, because inductor is an element that opposes the change in the current now. So that's why suddenly very high current will not flow. So please be careful. Even though all the four SCRs are in a conduction mode, this will not damage our source. This will not damage our supply because of this inductor. But if inductor is not there, and if all the four thyristors are in a conduction mode, definitely our source will get damaged. Are you getting the point? Okay. So because of this LS, our current, source current will not increase slowly, even though all the four thyristors are in a conduction mode. Okay. Now my question is, when all the four thyristors are in a conduction mode during this interval, that is a mu interval, what is the V0? Yes, can anyone? When all the four thyristors are in a conduction mode during that small interval mu, what is the V0 load voltage? It is like across the load we are having a short circuit na. So what is the V0? V0 is equal to 0, right? V0 should be 0, right? V0 is equal to 0 volt. So now with the effect of LS, can we draw the V0 waveform? I am saying with effect of LS. Okay. Can we draw the V0 waveform? Yes, V0 waveform with the effect of LS. Omega t 0 alpha. This is like this is alpha. This is like alpha plus mu, no? Because this angle is mu, overlap angle. Next, we are having a pi or pi plus alpha. Let me write directly. This is like pi plus alpha plus mu. Next, 2 pi or 2 pi. Yes, 2 pi to 2 pi plus alpha, and here it is supposed 2 pi plus alpha plus mu, right? Let us consider like this. Suppose this is a pi. So now during 0 to alpha, what is V0? During 0 to alpha, V0 will be negative, okay, as that of the previous case. Alpha to mu, all the four thyristors will be in on state na. During alpha to mu, alpha to alpha plus mu, all the four thyristors will be in on state, so V0 will be 0. Alpha plus mu to pi, V0 will be, yes, positive. Pi to pi plus alpha, it is negative, same as that of the previous case. Pi plus alpha to pi plus alpha plus mu, that is the mu angle is there, overlap angle is there. All the four thyristors are in a conduction mode. V0 is 0. Again at this instant, yes, it is a positive till 2 pi. Next, here it is a negative. Next, pi plus alpha to pi plus alpha plus mu, it is a 0. And again the same cycle repeats. So let me indicate here which thyristors are in a conduction mode. Alpha to alpha plus mu, all the four, that is T1, T2, T3, T4 are in a conduction mode, right? Alpha plus mu to pi plus alpha, only T1, T2. Pi plus alpha to pi plus alpha plus mu, all the four, T1, T2, T3, T4. Pi plus alpha plus mu to 2 pi plus alpha, only T3, T4. And again during this interval, yes, here it is a T1, T2, T3, T4. So similarly, yes, you can check 2 pi to 2 pi plus alpha T3, T4 na. So similarly here also T3, T4, right? So this is your Vs. This is your Vs. Are you getting the point, right? So here the thing is, due to the LS, yes, some overlap angle will be present. Overlap angle means during that angle, all the four thyristors will be in a conduction mode. All the four thyristors will be in a conduction mode. Sir, why does the current increase or decrease linearly? Okay, which you are saying here current is increasing slowly. Once it reaches the steady value, after that it will be constant, right?
Sir,
within a short term, we don't have much time, right? Please.
Yes, sir. From alpha, we are seeing that IS is increasing from negative value, no, sir. With LS. Rather from alpha, that zero crossing point, from there only, no, sir. Our IT1, IT2 should increase.
Where zero crossing point is? Where you are saying?
Zero crossing for IS is somewhere after alpha, no, sir. From there, our IT1, IT2 conduction must start, no, sir.
No, 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 no. It is not like that. You can check here. You can check here. At alpha, we are triggering T1, T2 na.
Sir.
So thyristor T1, T2 current starts increasing at alpha only,
Oh, okay, okay.
right? And at alpha, actually, we expect that the T3, T4 should turn off na. But
Okay.
whether at alpha T3, T4 current will suddenly become zero? No, it will decrease slowly na. So that's why it is like this.
But IS current was negative, no, sir. Will that have no effect?
Just a minute. You can check if you add this curve plus this curve na, you'll be getting this curve. Check here during 0 to alpha. During 0 to alpha, IT1, IT2 are 0. IT3, IT4 are I0. But we know if IT3, IT4 are positive means IS is negative na.
Yes.
So here it is I0, it is a minus I0.
No.
After that, what is happening? It is increasing, it is decreasing. At alpha, you can check. At omega t is equal to alpha, it is 0, IT1, IT2, and IT3, IT4 is I0 means this is minus I0. After that, yes, it is, this is decreasing and this one is increasing. Means in the source, what is happening? In the source or in the LS, what is happening? This current is like a negative current, na? That is downward current. Yes or no?
Yes, sir.
This decreasing current, IT3, IT4 current in a LS is like a downward current, na?
Yes, sir.
You can
Got
check
it,
here in LS, minus IS means what?
Yeah,
Downward
downward direction.
IT4, IT3, IT4 negative means IS is decreasing. IS is in downward direction, na?
Yes, sir.
Right? So that is what I'm saying. You can check here. When IT3, IT4 are decreasing means your downward current is decreasing. And your LS in upward current is increasing.
Okay,
So
sir.
you can in between we'll be having this type of waveform only. This point 0 means what it indicates? It indicates that here it is value and here it is value, means IT1, IT2 and IT3, IT4 both are the same values here. Now you can check IT3, IT4 positive means IS is negative na?
Yes, sir.
Now IT1, IT2 positive means IS is positive. So suppose consider the LS only, yes, upward current is suppose this much. Let us consider it as I0 by 2. Let me consider it as a I0 by 2, right? Suppose this is a I0 by 2 and this is also I0 by 2, right? Now you can check IT1, IT2 is I0 by 2 means current flowing through the LS in the upward direction, it is I0 by 2. At the same instant, IT3, IT4 is I0 by 2. The meaning is in the downward direction also we're having the I0 by 2 current na?
Yes, sir.
So what is the resultant?
Zero.
Result will be 0. So that's why it is a 0 here.
Okay, sir. Got it.
It is clear, right? So that's
Got
why
it.
the form should be like this only, right?
Yes, sir.
Okay, yes. So now, yes, we're having the V0 waveform. You can check this V0 waveform, that is with effect of LS, and the V0 waveform we're having without effect of LS. Yes, here it is. In the without effect of LS, there was a no zero portion in the V0 waveform, but here it is a zero portion is present. The meaning is, can we say that with the effect of LS, the average output voltage, yes, it will decrease? Yes or no? Right? Because the zero portion is there na. Now, can we derive the expression for the V0 average of this waveform? Yes, we can. Let me write V0 average with effect of LS, with effect of LS. So V0 average with LS. Now suppose we are having this waveform. Yes, you can check whatever the waveform we are having from omega t is equal to 0 to pi. The same is repeating na. It is negative, here it is also negative. It is 0, here it is also 0. Here it is positive, here it is also positive. Okay. So now can we write it as 1 by pi? So V0 average is equal to 1 by pi integration. Yes, integration. Now instead of taking integration 0 to pi, I will take it as from alpha to pi plus alpha, because 0 to pi means pi minus 0, same angle pi radian. Alpha to pi plus alpha, again it is pi plus alpha minus alpha, means again pi radian only. Okay. So now alpha to pi plus alpha, in that also the effective interval is alpha plus mu to pi plus alpha na? Yes or no, right? So let me write alpha plus mu to the pi plus alpha. Alpha plus mu to pi plus alpha. During this interval, what is the V0? V0 is the same as drop the supply voltage, right? So that is a Vm sin omega t. Sin of omega t into d omega t. Now can we simplify it? Yes, it is a Vm by pi. Integration of sin is minus cos of omega t. It is a alpha plus mu to pi plus alpha, which can be written as Vm by pi into, it is like a minus cos of pi plus alpha plus cos of alpha plus mu, right? So which this can be written as V0 average. Therefore, V0 average is equal to, yes, what is the cos of pi plus alpha? You can check 1, 0, minus 1. Cos of pi plus alpha is minus cos alpha, na? Right? Minus cos alpha. So it is Vm by pi into minus cos alpha and this minus. So it is a plus cos alpha. Okay. So it is a cos alpha plus cos of alpha plus mu. Cos of alpha plus mu. Right? This is your V0 average expression. This is the V0 average expression, right? Please don't raise the hand. We will discuss all your doubts at the end of the session. Right? This is the V0 average. This is with LS. This is with LS, right? So let me write here also with LS. Now, yes, if you check this circuit, in this circuit during the interval mu, that is from omega t is equal to alpha plus mu, it is like all the 4 thyristors are in a conduction mode, right? So now can we draw the equivalent circuit? Yes, from omega t is equal to alpha to omega t is equal to alpha plus mu during that interval only, as all the 4 thyristors are in a conduction mode. So can I say that it is like Vs, Ls, and across it is directly short circuit? Yes or no, right? So let me write it as during omega t is equal to alpha plus mu. Omega t is equal to alpha plus mu. Yes, we can draw the circuit like we're having Vs, we're having Ls, and across it is a direct short circuit because all the 4 thyristors are in a conduction mode. So this is Vs plus minus, this is Ls. Okay, and what current here is? This current is a Is, right? Now can we apply KVL to this loop? Yes, we can. KVL to loop, it is like a plus Vs minus Ls into dis by dt is equal to 0 now. So further we can write it as Vs means Vm sin omega t. Vm into sin of omega t is equal to Ls into dis by dt. Can I? Yes. Can we shift this dt to the left hand side? Yes. So therefore, Vm into sin of omega t into dt, which is equal to Ls into dis. Okay. Now we can integrate both these sides. Okay. Integrating both these sides. So it is like a Vm sin of omega t into dt, which is equal to integration of Ls into dis. Now, during this interval, we are discussing for alpha to alpha plus mu. Na? During this interval, angle is changing from alpha to alpha plus mu. So how the time will be changing? We are having the dt, na? Integration with respect to dt. So how the time will change? Time will change from alpha by omega to alpha plus mu by omega. Na? Yes or no? So let me put the limit here. Alpha by omega to alpha plus mu by omega. Yes or no? Because angle is nothing but omega into time, right? So again, how the current is changing during this interval, you can check alpha to alpha plus mu. How the Is is changing? Yes, we're having is, here it is. Alpha, at alpha, is is minus I0. At alpha plus mu means this instant, na, the is is plus I0. So is is changing from minus I0 to the plus I0. Okay, so let me write it as minus I0 to the plus I0. Now can we simplify it? Yes, it is a Vm into integration of sine is minus cos of omega t integration, right, with respect to time. So divided by omega should be there. Okay, alpha by omega to alpha plus mu by omega, right, is equal to ls into is, limit minus I0 to the plus I0. Now further we can write it as Vm by omega, Vm by, or let me take this ls also at this side. Okay, so Vm upon ls into omega. Okay, ls is a source inductance, Vm upon ls into omega, into, we can write it as a, put here limit, we need to put at for t only, na, because it is dt. Don't put this this limit for omega t. We need to put the limit for t only, right? So it is like a minus cos of omega into this term, alpha plus mu by omega, na? So omega cancel out. So it is alpha plus mu plus cos of alpha, na? Which is equal to ls into I0 plus I0, no? So further we can write it as, yes, so this can be written as Vm upon omega ls, or ls into omega you can write, into cos alpha minus cos of alpha plus mu, okay, is equal to ls into 2I0, 2 into I0 into ls. Okay, 2 into I0 into, sorry, ls we have taken already here, this cell. Okay, so this ls should not be there, right? We have taken this ls already here. So this ls, we cannot write here ls, right? So therefore you can check, it is only 2I0. Now from this, can we write cos of alpha plus mu expression? Yes, so therefore cos of alpha plus mu, let me shift this term to right hand side. So it is like, let me write directly, cos alpha minus 2 into omega ls into I0 divided by Vm, okay, is equal to cos of alpha plus mu. Please check. I've shifted this term to the right hand side. So it is omega ls into I0, okay, into 2 divided by Vm, and this term again to the left hand side. So cos alpha minus that term, and this term to the right hand side. Okay, so this expression is important in order to find the mu value, overlap angle value. Okay, this expression is important, right? Next, now you can check, consider this as equation number 2, and here we are having the V0 average, consider it as equation number 1. Here also we are having cos of alpha plus mu, and here we are having the expression for cos of alpha plus mu. Can I put equation 2 in this equation 1? Yes. So let me put equation 2. Put equation 2 in equation 1. So we can write V0 average. Therefore, V0 average is equal to what? Vm by pi into, it is a cos alpha, na? Next, it is a plus cos of alpha plus mu, no? Right? So plus cos of alpha plus mu is this term. So we can write it as cos alpha minus 2 into omega ls into I0 divided by Vm. Right? So cos alpha plus cos alpha, it is a 2 cos alpha. Okay, so let me write it as a Vm by pi. Therefore, V0 average is equal to Vm by pi into, we can write it as 2 cos alpha minus 2 omega ls into I0 by Vm. 2 into omega ls into I0 divided by Vm. Right? Further, can we take these 2 outside? Yes. Okay. So therefore, V0 average is equal to 2 Vm divided by pi into, it is like a cos alpha minus omega ls into I0 divided by Vm. Right? Now, what is the V0 average without the effect of LS? Suppose same circuit, single phase fully controlled bridge rectifier, REL load, continuous conduction. What is the V0 average without the LS? It is a 2 Vm by pi into cos alpha, na? Yes or no? Are you getting the point, right? So let me write, therefore V0 average is equal to 2 Vm divided by pi into cos alpha minus, again we can multiply this term into this bracket. So Vm will get cancelled out. So that will be like here 2 into omega into Ls into I0 divided by pi. Okay. And what this term indicates, 2 Vm by pi into cos alpha means here your V0 average without the effect of Ls. Are you getting the point? Okay. So therefore V0 average is equal to, let me write it as a V0 average without Ls minus 2 into omega into Ls into I0 divided by pi. What this equation indicates, can we say that due to the Ls, okay, the voltage drop in the output voltage, okay, is nothing but this value. Are you getting the point? This is without the effect of Ls minus this value, na, is nothing but your V0 average, right? So that's why it is a, yes, this value indicates your voltage drop due to the Ls. This indicates your voltage drop with the Ls. Are you getting the point, right? So as long as numericals are considered, this expression is important. As long as objective type questions are considered, this expression is also important. They have asked, okay, what is the effect of Ls? Okay, what is the voltage drop that is causing with the Ls? So voltage drop is 2 into omega Ls into I0 by pi, because it is a minus, na? So without Ls minus this drop is nothing but your V0 average with Ls, V0 average with Ls, right? Okay, so next, again, this expression is also important, right? Okay, so this is the effect of Ls on the performance of single phase full bridge rectifier. Okay, single phase full bridge rectifier, and the effect of Ls will be observed when the load is highly inductive. Then and only then we can observe more effect. Okay, so that's why we consider this case here, right? Now let us discuss the numericals. Please go through this theory. Okay, it is very simple. The only thing is we need to yes, stick with the basics. Actually, what is the effect of Ls? It opposes the change in the current. If you understand Ls opposes the change in the current, definitely you will understand due to the Ls your Is will be getting affected, your IT1 IT2 will be getting affected, IT3 IT4 will be getting affected, right? So that's why without Ls we are having this type of waveform. Sudden changes there possible in IT1 IT2 as well as IT3 IT4 as well as your Is, but whereas if you check with Ls, sudden change is not possible. So therefore your IT1 IT2 is increasing slowly, IT3 IT4 will decreasing slowly. So due to that, yes, one is increasing, one is decreasing. All the four thyristors will be in a conduction mode. So that's why resultant voltage will be like this. Okay. Yes. So now let us discuss some numericals. Yes, here it is. A single phase full converter circuit is shown in figure. Assume the load current is a constant and power delivered to the load is a 3 kilowatt. Load power is given, it is a 3 kilowatt. The converter is operated at alpha equal to 30 degree. The RMS value of fundamental component of source current in ampere is. Our task is to find the RMS value of fundamental component of source current. Means IS1 RMS we need to find. We need to find the IS1 RMS. But the thing is, here they have given the LS. Here they have given the LS. Okay. So now with LS, what is the source current waveform? Just now we have discussed. Okay. Just now we have discussed. So here, let us first note the data. P0 load power, that is the real power, 3000 watt. alpha is given, it is a 30 degree, and our task is to find RMS value of fundamental component of source current. Okay, I0 is constant na, I0 is equal to I0, and our task is to find IS1 RMS. We need to find the IS1 RMS, right? Now, in order to find the IS1 RMS, okay, yes, how is the waveform of IS? Yes, you can check. This is 230 volt given. Converter operated, okay. RMS value of fundamental component of source current, okay. This is 230 volt supply voltage. Vs is 230 volt. It is a pure sinusoidal. They have indicated na sinusoidal. So it is a pure sinusoidal. And frequency is a 50 hertz. Frequency is a 50 hertz, right? Now, yes, can we draw the IS waveform? Can we draw the IS waveform by considering this effect LS? Yes or no, right? So IS waveform by considering the effect of LS. Just now we discussed that IS waveform. Omega t 0, 0 to alpha, alpha to alpha plus mu to pi, pi to pi plus alpha, pi plus alpha to pi plus alpha plus mu, pi plus alpha plus mu to 2 pi, and 2 pi to 2 pi plus alpha. Two pi plus alpha, and again the same will repeat, right? Okay. So waveform is like this. You can check 0 to alpha IS is negative. T3, T4 will be in a conduction mode na? At alpha, from alpha to alpha plus mu. Yes, IS will be increasing slowly na? IS will be increasing slowly. So at alpha plus mu, it will be reaching the plus I0. This is a minus I0. Here it is a plus I0. Okay, it is a plus I0. After that, from this instant to pi plus alpha, it will be constant current. This is a I0. At pi plus alpha to pi plus alpha plus mu, it will be decreasing, na? Right? So it will be decreasing due to the presence of LS, right? And again, it is a constant current till 2 pi plus alpha, and again it will be increasing slowly this type. Next, it will be constant. Okay, so it is like a minus I0 here, right? And here it is a plus I0, right? So this is the IS waveform we're having. This is the IS waveform we're having. Next, how is the VS waveform? VS is a sinusoidal. We know it is a VS given sinusoidal. It doesn't matter alpha plus and those things. Okay, so VS is like this. This is a pi, na? Okay. It is a pure sinusoidal, right? Same. Pi 2 pi 2, right? Why I have drawn the VS and IS waveform? Because we require the angle between the two, na? Angle between VS and IS. Okay. So now next. So if you check P0, they have given it is a 3000 watt. P0 is equal to 3000 watt. Load current is a constant, that is a I0. So if the load current is constant, what is a P0 or P0 average? If load current is constant, what is a P0 average? Yes, it is a V0 average into I0, na? Yes or no? Yes, okay, it is a V0 average into I0. Yesterday we discussed. Okay, so let me write here P0 is equal to 3000 watt. So therefore here we can write V0 average into I0 is equal to what? It is a 3000 watt or 3000. So therefore can I write V0 average is equal to 3000 divided by I0. 3000 divided by I0. Next, now with the effect of LS, whether we are having the expression for V0 average in terms of I0, you can check with the effect of LS whether we are having the expression of V0 average. Yes, this is in terms of alpha plus mu, and the second one is in terms of, yes, this is the V0 average we are having. Yes, you can check V0 average 2 Vm by pi into cos alpha minus 2 into omega Ls into I0 by pi, right? So can I use this expression there? Because V0 average we can replace with a 3000 divided by I0, right? Here also I0 we need to find. Ls they have given, omega we can find, alpha they have given, okay? And it is 2 Vm by pi. Vm is given, okay? So let me write with effect of Ls, it is a V0 average. Let me, yes, use this expression. Yes, right? I'm using this expression here. So you can check here. Yes. So in V0 average, can we replace it with 3000 by I0? Yes, 3000 divided by I0 is equal to 2 into Vm. What is Vm? It is a 230 into root 2. Na? So it is 2 into 230 into root 2 divided by pi into cos of alpha. Alpha they have given. It is a 30 degree. Minus 2 into omega. Yes, what is the frequency? 50 hertz. So omega is 2 pi f na. So it is 2 pi into 50. Into Ls. Ls they have given 1.4 millihenry. Into I0. I0 we need to find divided by pi na. Divided by pi. Right? Now one equation we are having and one unknown na I0. So can we find the value of I0? Yes, we can find. Okay. So here we can write it as, let me multiply both these sides with the I0. Okay. Or take the, simply take the cross multiplication. Right? So let me write as, or first simplify it, 3000 divided by I0 is equal to, this term will be cost 30, 179.33, right, minus this term. .28. Right, now we need to find the value of I0. Okay, so we can write it as 3000 is equal to 179.33 into I0 minus 0.28 into I0 square. Na? So further we can rearrange the term. Therefore 0.28 into I0 square minus 179.33 into I0 plus 3000 is equal to 0. Na? So now from this, can we find I0? Yes. So therefore I0 is equal to minus B. So minus minus plus 179.33 plus minus under root B square minus 4AC. 179.33 square minus 4 into AC. 0.28 into 3000 divided by 2A. Please check how much you are getting. Yes, please check what is the I0 we are getting. Here I0 is constant because they have given it is a constant current source na at the load. The meaning is your load current is constant. Are you getting the point? right? So please keep it in mind. Yes, what is the I0? $17.19. How you are getting 0 ampere? Yes, 17.19. 17.19. This is your I0. Is this clear? This is the I0 we're getting. Now we know the I0. Can we find the mu value? Overlap angle mu, right? So you can check overlap angle mu. So for that we can use this expression, whatever we derived. Yes, here it is. Cos of alpha plus mu is equal to cos alpha minus 2 omega ls into I0 by Vm. Na? So from this, can we find mu? I0 we have calculated, so we can find the mu, right? So it is a cos of alpha plus mu, also cos of alpha plus mu is equal to, yes, cos alpha minus 2 omega ls into I0. Also cos of alpha plus mu is equal to cos alpha minus 2 omega ls into I0 divided by pi, na? So I0 divided by Vm divided by Vm, right? So now in this we can write, therefore cos of alpha is 30, na? Plus mu is equal to cos 30 minus 2 into 2 pi f into ls. Ls is 1.4 into 10 to the power minus 3 into I0. It is 17.19 divided by Vm, 230 into root 2. Please check what is the mu we are getting. From this, please find the mu value, overlap angle mu. Okay. Shreyas, two values we are getting, na? I0 17.19 and 623.50. Okay. But generally select the lower value. Okay, select the lower value, because you can check 623.50 is a very high current, right? So we need to select the lower possible value. Yes, 4.96 is the mu, na? So it is a roughly 5 degrees Celsius, 5 degree, not Celsius, 5 degree. This is a mu, that is a overlap angle. Now mu we know, right? Our task is to find the IS1 RMS. Okay, IS1 RMS. Now from this, can we write, yes, real power, input real power, or the active power, input active power is equal to load power. Because in our circuit we don't have any other element to consume the energy, to consume the power, right? So whatever the real power we are having, that is equal to your load power. Okay, so what is the input active power? It is a VS1 RMS into IS1 RMS into cosine of angle between two, na? Cos of angle between these two. So it is a cos of angle between VS1 and IS1 is equal to load power, that is a P0, and load power is your active power only, yes or no, right? So what is VS1 RMS? It is a 230 into IS1 RMS into, here please listen how to find this angle. This is important here, how to find this angle. Please check the IS waveform and VS waveform. For that only we have drawn the VS and IS waveform. Okay, so yes, here Vs is equal to Vm sin omega t, na? Vs is equal to your Vm into sin of omega t. Now if you recall yesterday's session, we have written the expression for IS1, for a 180-degree square wave mode. For a square wave mode, I am saying, okay, not for the quasi square wave, for the square wave. If you recall the IS waveform in the yesterday's session, okay, whatever we drawn, it was like from omega t is equal to 0 to alpha, IS was minus I0. Na? At alpha, yes, there was a sudden increase in the IS from omega from minus I0 to the plus I0. And after that, from alpha to pi plus alpha, IS was only plus I0. At pi plus alpha, IS was changing from plus I0 to the minus I0, right? So this type of waveform we were having, okay? So now in that case, what was the angle between VS1 and IS1 we got? It was a cos alpha, na? Right? Means VS was like this only, and IS was a square wave, and zero crossing of the IS, it was at omega t is equal to alpha. So with that logic, now suppose in that case, yes, the angle was a cos of alpha. Now here you can check, here it is a Vm sin omega t. And can we find this angle of zero crossing for IS? What is this angle of zero crossing, or at which angle IS is having a zero crossing? This alpha, this total is mu, na? From here, yes, between these two are having a mu. So can we say that this is exactly passing through the center of this mu? So what is this angle? This angle is like your alpha plus mu by 2. Are you getting the point? This alpha will remain as it is, and this mu will be, here it is mu by 2, and at this side the mu by 2 will be there. So the angle is alpha plus mu by 2. In the yesterday's session, we discussed the IS was IS was having a zero crossing at omega t is equal to alpha. Yes or no? Here IS is having a zero crossing at alpha plus mu by 2. Okay. So now we can, yes, consider the angle between these two is equal to alpha plus mu by 2. Okay, alpha plus mu by 2. Actually, the current is lagging to voltage by how much angle? Alpha plus mu by 2. Alpha plus mu by 2, right? So let me write here, cos of alpha plus mu by 2 is equal to P0, that is a 3000. So now from this, can we write IS1 RMS? Yes, it is equal to, please check once. IS1 RMS. I am getting the difference between quasi square and square waves. Quasi square means square wave which is having in between a zero values, na? Some zero interval is present. That is a quasi square wave. Yes, I will repeat the zero crossing. Yes, what is IS1 RMS? It is 15.46. Is this correct? 15.46 ampere. Okay. This is your IS1 RMS. Please listen how to find this zero crossing. This is very important. Yes. You can check at alpha, IS is minus I0. After this point, okay, it is a non-zero positive value, IS. So zero crossing means what? At this instant, it is having a zero crossing, na? So you can check this angle is alpha, and what this angle is, this small angle is, like your mu by 2, na? This small angle is a mu by 2. So what this angle indicates, I'm saying this angle. Yes, what this angle indicates, it is a alpha plus mu by 2, na? Right? So that's why here I have written it is a cos of alpha plus mu by 2. Alpha plus mu by 2. You can check yesterday's sessions. IS was having a zero crossing at alpha. So angle was cos alpha. Here IS is having a zero crossing at alpha plus mu by 2. So that's why the angle is alpha plus mu by 2 here. Right? So correct. Okay. So 15.46. Is this clear? So this is your IS1 RMS. Okay. So please go through the numerical, how to find the IS1 RMS, right? This is the numerical they asked in one of the examination, right? So next, Let us discuss the next question. Yeah. The figure below shows an uncontrolled diode bridge rectifier supplied from a 220 volt 50 hertz single phase AC source. The load draws a constant current I0 is equal to 14 ampere. One more thing. If they indicates the load with a constant current source, na, then the meaning is your load current is constant. Okay, load current is constant, right? Next, the conduction angle of the diode D1 in degree rounded up to 2 decimal places is. Now here we are having a diode bridge rectifier. Diode bridge rectifier and thyristor rectifier, what is the difference? Alpha equal to 0 in thyristor rectifier means your diode rectifier, na? Yes or no? Right? Always keep it in mind. In controlled rectifier, if we put alpha equal to 0, we'll be getting the diode rectifier. We'll be getting the diode rectifier. Now, yes, first of all, note the data. In this case, we're having Vs is 220 volt. Vs is equal to 220 volt. RMS value they have given. Frequency is a 50 hertz. I0 is a constant current. 14 ampere. Conduction angle of a diode we need to find. Conduction angle of a diode D1. Yes. So my question is, suppose if the LS is not present, okay, so what will be the conduction angle of diode D1? My question is, if the LS is not present, then what will be the conduction angle of diode D1? Here I0 is constant, means simply consider the load is highly inductive. Consider the load is highly inductive. Okay. So if LS is not present, then conduction angle of diode will be, it is a pi, na? I am saying that conduction angle, not the firing angle. Some are saying 0. How the conduction angle of diode will be 0? Right? It is a pi. Conduction angle is a 180 degree, na? At suppose if this LS is not present, I am saying LS is not present, then at omega t is equal to 0, these two will be turning on, right? So these two will be turning on, these two will be turning on at omega t is equal to 0. So from omega t is equal to 0 to pi, current will be flowing from supply D1 load D2 and again back to the Vs. At pi, these two will turn off and these two will conduct, na? So from 0 to pi, D1 D2 conducts. Pi to 2 pi, D3 D4 conducts. This is true when your inductance, source inductance is absent, but now the source inductance is present. So now my question is, due to the source inductance, whether the conduction angle of diode will increase, that is, it will be more than 180 degree or it will be less than 180 degree. Due to the presence of source inductance, whether the conduction angle of diode D1 will increase or will decrease. Same. Okay. Increase, decrease. Okay. Listen it carefully. Same effect of LS theory we need to use here. Okay. So suppose if I want to draw the waveform for this circuit, how it will be? Right. So I am writing without that thing, without LS I am writing. Okay. Without LS, let me first draw ID1 waveform. 0 to pi, pi to 2 pi, 2 pi to 3 pi, right? Without LS, without LS. If LS is not present, then what about the ID1 from omega t is equal to 0 to pi? ID1 will be, come on, speak out. From omega t is equal to 0 to pi, what will be the ID1 in this circuit? Without LS, I am saying, suppose LS is not present. 0 to pi, what is ID1? ID1 means current flowing through the diode D1, ID1. Come on. I0, right? It is a I0 only. Good. So it is a I0 means ID1 will be I0. This will continue till pi, right? This is a I0. Next, at pi without ls, whether ID1 will suddenly decrease to 0 or it will decrease slowly. Come on. At omega t is equal to pi, whether ID1 will decrease suddenly at 0 or it will decrease slowly without ls. Without ls, it will decrease suddenly, na? So that's why here ID1 waveform will be like this, na? From pi to 2 pi, whether diode D1 will be in a conduction mode? No. Pi to 2 pi, diode D3 will be in a conduction mode, na? So that's why from pi to 2 pi, it will be 0. From 2 pi to 3 pi, again the same cycle repeat. Yes or no? Right? So this type of waveform for ID1 will be getting. Now with ls, what is the change? With ls, what will be the change? Come on. ID1 waveform with ls. Yes, whether at 0, the current ID1 will increase suddenly or it will increase slowly. At omega t is 0, ID1 will increase slowly or it will increase suddenly due to the ls. Slowly, yes or no? It will increase slowly, na? Right? At 0, it will increase slowly. So the waveform will be like this. Next, it will be steady value till pi. At pi, whether it will decrease suddenly? No, it will decrease slowly, na? So it will be like this. At 2 pi, again, it will increase slowly, steady value, and again it will decrease. Is this clear? So what this indicates your slowly increase means, definitely this will be your I0, and this indicates your mu. This indicates your mu. Yes or no? Now they have asked the question, what is the conduction angle of diode D1? Initially, without ls, diode D1 was conducting only for 0 to pi. Now you can check with ls, the diode D1 is in a on state from 0 till this instant, na? Yes or no? So can we say that the conduction time of diode D1 with ls is equal to what? This is a pi actually. This is pi plus this mu, na? Are you getting the point? Okay. So with ls, the conduction time or the conduction angle of diode D1 is a pi plus mu. Is this very clear to all? Right? Without ls, it is a 180 degree, no problem. But with ls, it is a 180 degree plus mu. 180 degree plus mu, right? So now ultimately what we need to find? We need to find the mu only, na? Because 180 degree is a constant, right? So we need to find the mu. Now how to find the mu? We know I0 they have given, ls they have given, frequency they have given. So thing is we need to find the mu only, right? So alpha is in this case, it is a 0 only, right? So can we use that expression? Yes, cos of alpha plus mu. Let me write that expression. Yes, this expression as it is. Yes. Yes. So now you can check here. In this expression, it is a diode rectifier, so alpha is 0 degree. Okay, so alpha equal to 0 degree because diode rectifier, right? So can I write cos of 0 plus mu means mu is equal to cos of 0 minus 2 into omega ls. What is omega? 2 into pi into frequency. Frequency they have given, it is a 50 hertz into 50 into ls, it is a 10 millihenry. 10 into 10 to the power minus 3 into I0, it is a 14 ampere, na? 14 divided by Vm. What is the Vm? 220 into root 2, na? So it is a 220 into root 2. So please check what is the mu here, right? Please find the value of mu. Yes, what is the mu value? 44.17 degree, right? 44.17, correct? 44.17 degree means the mu value is 44.17. So what is the conduction angle of diode? So therefore, conduction angle of diode is equal to 180 plus mu. So it is equal to 180 plus 44 point. Yes, this is a 17 is equal to 224.17 degree, right? Correct. So this is a conduction angle of diode, right? Okay. To 24.17, correct? Okay, okay, okay. Anonymous attendee, right? Tomorrow's schedule we cannot cancel. Okay, tomorrow morning we'll be having the class 6:30 to 9:30 power electronics instead of T and D. Okay, and at the evening also 5 to 9 we'll be having the power electronics session. Next, let us discuss the one more numerical, and after that we'll take a break. So a midpoint rectifier is shown in the figure where we assume the transformer to be ideal and the DC side load to be represented by a current source. Okay, DC side load is a constant, that is a capital I0. The ratio of volt ampere rating of transformer to the average power supplied by the load is, okay, means we need to find the ratio of VA rating of the transformer, right, to the P0 average. To the P0 average we need to find. Now here important thing is, here for this numerical, if we use the machine theory, that is VA rating at the secondary side is equal to VA rating at the primary side, okay, we will not get the options here, answers we will not get. Okay, so here we need to find the VA rating of the transformer is equal to VA rating of primary plus VA rating of the secondary divided by 2. Okay, divided by 2, that we need to do here. Okay, so let us discuss how to simplify. Load current is a constant they have given. It is a diode rectifier. Here it is a diode rectifier. Let us consider current here is, sorry, voltage here is Vs. It is a N/1 transformer na? So if it is Vs means definitely here it is a Vs by N. Definitely here it is a Vs by N. Yes or no? What is the meaning of this N/1/1? If this is Vs, there at the upper part of the secondary is equal to Vs by N. At the lower part of the secondary is equal to Vs by N. So Vs is here Vs by N, here it is Vs by N. Okay. Now first of all, can we find the P0 average, that is the average power of the load. Okay, P0 average. Let me write P0 average is equal to, now here load current is constant na? Load current is constant, so what will the P0 average? Come on, what will be the P0 average? V0 average into I0 na? Yes or no? V0 average into I0. Okay, so because load current is constant na, right? So it is a V0 average into I0 right? So now here, how to find the V0 average? It is a diode rectifier. The meaning is from omega t is equal to 0 to pi. Omega t is equal to 0 to pi. V0 is same as of the supply voltage. Pi to 2 pi, again we'll be getting the positive cycle only for this load. Okay, so we'll be getting V0 like this. In the thyristor rectifier, put alpha equal to 0 degree, right? So we'll be getting this type of waveform now. This is a pi, this is a 2 pi, this is a 3 pi, right? So 0 to pi, 2 pi, pi to 2 pi, 2 pi to 3 pi. So we'll be having this type of waveform. This is a Vs only, but not Vs. Here it is Vs by N. So definitely it should be Vs by N here, right? Next, now can we find the V0 average? Yes, V0 average is equal to 1 by pi integration from 0 to pi It is a Vs by n. Be careful. At the primary we are having Vs. At the secondary we are having the Vs by n. Huh? Okay. So integration from 0 to pi. It is a Vs by n. Okay. That is nothing but Vm into sine of omega t. Right. Divided by n into d omega t. Na? Vs means pure sinusoidal. Vs by n means this sinusoidal divided by n. Okay. Now can we simplify it? Therefore, V0 average. Okay. Yes. So therefore, V0 average is equal to, we can write Vm by n pi into, yes, integration of sine is minus cos of omega t. Limit 0 to pi. Okay, so if you put the limit, you will be getting it is 2 Vm by n pi. Na? This is the V0 average. 2 Vm by n pi. Now, therefore, what is the P0 average? V0 average into I0. Na? So it is 2 Vm divided by n pi into I0. 2 Vm by n pi into I0, right? 2 Vm by n pi into I0, right? So this is a P0 average. Next, now what about the transformer VA rating we need to find? So for that, we need to find the VA rating of the transformer at the primary side and at the secondary side. So let us first find the VA rating of the transformer at the secondary side first. At the secondary, we're having, yes, upper part, and here it is a lower part. Okay, so upper part here it is, and here it is a lower part. So overall transformer VA rating at the secondary side is equal to VA rating of either upper part or the lower part into 2. Okay, so either we can find the VA rating of the upper part and we can multiply it with the 2 to get the VA rating of the secondary part. Okay, secondary side of the transformer, right? So let me write VA rating of transformer. VA rating of a transformer is equal to primary VA plus secondary VA divided by 2. Okay, divided by 2, right? So now here we need to write, yes, secondary VA. Secondary, let me write first upper part we can find. Upper part or upper half part, you can say upper part VA rating is equal to what? How to find the secondary upper part VA rating is equal to secondary upper part voltage RMS value into secondary upper part current RMS value. Yes or no? Right? So let me write it as, yes, secondary upper part voltage RMS. This is the one thing, into secondary upper part current RMS. RMS. So let me write, yes, what is the secondary upper part voltage? It is a Vs by n. You can check here. It is a Vs by n, right? And what is the current? You can check the current. Let me consider this current as a IS1. Let us consider it as a IS1. Okay. This is not a fundamental. IS1 means the upper part, secondary upper part current. That is a IS1. Okay. So let me write it as IS1. So how is the IS1 waveform? IS1 waveform we can check omega t 0, 0 to pi and pi to 2 pi, right? So you can check this circuitry. This diode will be in a conduction mode only from omega t is equal to 0 to pi. Na? So during 0 to pi, what is the current that is flowing into this winding, upper part of the secondary winding? It is a I0, na, load current, right? So can we draw the waveform as, this is a I0 from pi to 2 pi, from omega t is equal to pi to 2 pi, whether the current will flow into the upper part? No, current will be flowing into the lower part. Na? In this part, the current will be flowing because pi to 2 pi supply voltage is negative. Na? So this type of waveform will be getting, right? So therefore here current will be 0. Here current will be 0, and again the same will repeat. What is this value? This value is a I0. This value is a I0. Now, can we find the RMS value of this IS1? Yes, IS1 RMS is equal to 1 by 2 pi. Yes, integration from 0 to pi I0 square into d omega t to the power 1 by 2. So is equal to I0 divided by root 2 pi into root pi. So it is like I0 by root 2, right? I0 by root 2. Okay. So let me write it as IS1 RMS is I0 by root 2. So therefore, secondary upper part VA rating is equal to Vs by N into this current, na? That is I0 by root 2. I0 by root 2. So therefore, what is the VA rating of full secondary winding? That is a 2 into this part. So therefore, VA rating of secondary winding is equal to 2 into Vs by N into I0 by root 2. So it is equal to root 2 into Vs into I0 divided by N. This is your VA rating of secondary winding. Okay, VA rating of secondary winding. Next, now can we find the VA rating of the primary winding? Yes, primary winding VA rating. Primary side VA rating of transformer. Yes, is equal to primary side voltage RMS. Primary side RMS voltage into primary side RMS current. RMS current, right? So let me indicate the primary side current as IP. Let me indicate this current as IP. Okay. Now, can we draw the IP waveform? Can we draw the IP waveform? Yes, IP waveform. It is primary side current waveform. 0 to pi and pi to 2 pi. You can check during 0 to pi, the secondary current is, it is a I0, na? Right? So if the current in the secondary is I0, it is for N/2 1/1 transformer, na? So what about the current that will be flowing at the primary side? If this part current is your I0, then here current will be like, for the voltage, if it is step down, na, for current it is a step up, na? Yes or no? Means this current will be higher, this current will be lower. So it will be like your I0 by N. Okay, I0 by N. So IP waveform will be like this. It is I0 by N, 0 to pi, and pi to 2 pi, it is a negative current, and the value will be I0 by N. This is the I0 by N, and here it is also I0 by N. Are you getting the point? Voltage is step down, current is a step up, na? If this is I0 by N, this is I0 current, right? Step up current like this. So we'll be getting this type of waveform. Okay. So this is the IP. Now what is the RMS value of this current? Yes, primary side RMS current, that is IP RMS. I'm writing here. It is same I0 by N only. I0 by N only, right? Next, so therefore primary side VA rating. Yes, primary side VA rating. Is equal to, we can write Vs, because primary side voltage is Vs, we considered, na? This is Vs. And what is the current? Just now we written. It is a I0 by N. I0 by N. Okay. So therefore we can write transformer VA rating. Transformer VA rating is equal to Vs into I0 divided by N plus, what is the secondary we have written? Root 2 into Vs into I0 by N divided by 2. So if you check, it is equal to, we can take Vs I0 by N outside, na? So it is like 1 plus root 2 divided by 2. Okay, 1 plus root 2 divided by 2. So which is equal to 1.207 na? Vs, sorry, 1.207 into Vs into I0 divided by N, right? This is your transformer VA rating. So now, if this is transformer VA rating, then what is the ratio? So therefore, ratio means they have asked for volt ampere rating of the transformer divided by average power supplied. Okay, so therefore, transformer VA rating divided by P0 average, which is equal to 1.207 into Vs into I0 by N divided by what is the P0 average? Yes, we have written here P0 average 2 Vm by N pi into I0, right? 2 into Vm divided by N pi into I0. No? So you can check here. I0 will get cancelled out. Further, can we replace this Vs with Vm by root 2, or can I replace this Vm with root 2 into Vs? Yes, so that they will get cancelled out. 1.207 into Vs, N also will get cancelled out. Okay, into Vs divided by, it is a 2 into root 2 into Vs, right, divided by pi. So this divided by pi will be shifting in the upward. That is the numerator side. So Vs will get cancelled out. So if you check, it is 1.3406, right? This is your transformer VA rating divided by P0 average, right? P0 average. Yes. Is this clear? Right. So, okay. Please keep it in mind. Transformer VA rating, okay, is you can represent in both the VA rating. If they ask, then we need to write in this way. Okay, that is a primary VA plus secondary VA divided by 2 divided by 2, because the thing is, at a time through secondary both the parts the current is not flowing here, but whereas in the machines we generally consider it as a same current is flowing na. So that's why there is a different thing, right? So please be ready with the two expressions, as this one as well as if both are same, right, means if primary VA is equal to secondary VA, right? But if you solve this numerical with that thing, okay, that is the primary VA is equal to secondary VA, you will not get the correct answer, right? So okay, so we'll take a break here, and we'll start at 7:28, right? 7:28. After the break, we'll be discussing about the three-phase rectifiers. Okay, three-phase rectifiers. Okay. All right. So now we are going to discuss a three-phase rectifier circuits. In the three-phase rectifiers, we are going to discuss a three-phase, three-pulse uncontrolled rectifier, three-phase, three-pulse uncontrolled rectifier, three-phase, three-pulse controlled rectifier. Uncontrolled means diode rectifier and controlled means a thyristor rectifier. Okay. Third, three-phase, six-pulse uncontrolled rectifier. Three-phase, six-pulse controlled rectifier. And three-phase semi-converters. Okay. So these five circuits we are going to discuss. Three-phase, three-pulse uncontrolled means it is a three-phase half-wave rectifier. Okay. Three-phase, three-pulse means three-phase half-wave. Three-phase, six-pulse means three-phase full wave. And apart from these two, we are having a three-phase semi-converter also, just like a single-phase semi-converter. Okay, we are having a three-phase semi-converter, right? Three-phase semi-converter is again a three-phase full wave rectifier only. Okay, three-phase full wave rectifier only. So let us first discuss three-phase, three-pulse uncontrolled rectifier. Three-phase, three-pulse uncontrolled rectifier. Yes. Three-phase, three-pulse uncontrolled rectifier. The three-phase, three-pulse, the meaning is corresponding to one input cycle. In the output, we are getting the three pulses. So that's why it is a three-phase, three-pulse. Okay. Three-phase means three-phase input supply. And three-pulse means corresponding to one input cycle, okay, of the supply. In the output, we are getting the three pulses. So that's why it is a three-phase, three-pulse. So here, if the supply frequency is your 50 hertz, the output pulse frequency is equal to 3 times the supply frequency. That is a 3 into 50 means a 150 hertz. Okay, that is a 150 hertz. So please be careful. Single phase half wave means single phase single pulse. Single phase full wave means single phase two pulse. Three phase half wave means three phase three pulse. Okay, so please try to understand this, right? So three phase three pulse uncontrolled rectifier. Uncontrolled rectifier means a diode rectifier. So let us first draw the circuit diagram for three phase three pulse uncontrolled rectifier. Okay, so here, yes, we're having a three phase transformer. The primary of the transformer, it may be a star connected or it may be a delta connected, right? Primary of the transformer, it may be star connected or delta connected. The input to this transformer at the primary side is a balanced supply, right? What do you mean by the three-phase balanced supply? Three-phase balanced supply means in a three-phase supply, all the three line voltages, okay, will be having the same RMS value. All the three line voltages will be having the same peak value. All the three line voltages will be having the same frequency. Are you getting the point? And at the same time, all the line voltages will be displaced by 120 degree. Okay, all these points will be applicable for the phase voltages also, will be applicable for phase voltages also. So which points I told you? Yes, RMS value same, peak value same, frequency same, and the phase displacement should be 120 degree. Okay, that is nothing but your balanced supply. That is nothing but the balanced supply, right? So here it is a transformer primary, it is connected in star, connected in delta. It may be connected in star or delta. Primary may be connected in star or delta, but transformer secondary required for this type of rectifier, yes, it should be connected in star only. Okay, so transformer secondary winding we require, yes, it should be connected in a star only. So suppose this is the one winding, second winding, and here it is a third winding. Yes, one diode is connected here, second diode, and here it is a third diode, right? Suppose load is a purely resistive, right? After this, we'll discuss for RL load, right? Or RLE load. R load, this voltage is V0, this current is I0, right? Diodes are considered as a D1, D2, D3. Consider this current is ID1, ID2, and this current is ID3. Yes, this is the neutral point. This voltage is, suppose it is a VA, or let me write it as a VAN. This is a VBN, and here it is a VCN. That is a phase A voltage, phase B voltage, and phase C voltage. Okay, now, yes, here, if you check, we are having the three diodes, and at a time only one diode will be in a conduction mode. At a time only one diode will be in a conduction mode. Okay, so suppose when D1 is in a conduction mode, how the current will be flowing? Current will flow from like VAN, D1, load, and again back to the neutral point. When D1 is in a on state, which diode will be in a conduction mode? Okay, that we are going to discuss. But the thing is, at a time only one diode will be in a conduction mode. So when D1 is in a conduction mode, current will be flowing like VAN, D1, load, and again back to the neutral point. In this loop, the current will be flowing. So you can check if the current is flowing into this loop, what is the voltage across the load? The voltage across load is nothing but your voltage across the phase A. Similarly, when diode D2 will be in a conduction mode, current will be flowing like VBN, D2, load, neutral point, right? And again back to the VBN. Means in this loop, the current will be flowing when D2 is in a conduction mode, I am saying. Okay. So what is the V0? V0 is equal to VBN. When D3 is in a conduction mode, current will be flowing like VCN, D3, load, and again back to the neutral point. In this loop, the current will be flowing. So what is the V0? V0 is equal to VCN. So here you can check. As I said, at a time only one diode conducts. Okay. And when one diode will be in a on state, the voltage across the load will be getting is nothing but your phase voltage only. Na? When D1 conducts, we are getting in the load, which is equal to VAN. When D2 conducts, V0 is equal to VBN. When D3 conducts, V0 is equal to VCN. What is the VAN, VBN, VCN? These are the line voltages or phase voltages? These are the line voltages only. Yes or no? Sorry, these are the phase voltage, not a line. These are the phase voltages only. Okay. So that's why please try to understand when at a time only one diode is in a conduction mode, the load voltage is nothing but a portion of that respective phase voltage. Okay. So that's why in this rectifier, that is a three-phase half-wave rectifier, if you check the supply voltage waveform, the supply voltage waveform is nothing but three-phase balanced voltage supply. Okay, three-phase voltage supply, three-phase balanced voltage supply. Okay, I am saying that at a time only one diode is in a conduction mode. When one diode conducts, then voltage across the load is nothing but the respective phase voltage only, some portion of the respective phase voltage only. Okay, So that's why in the supply system, this is your supply. This is the supply system. So in the supply system here, we're having the three-phase voltage waveform. We're having a three-phase voltage waveform only. Okay. So which are these three-phase voltages? Let me indicate. This is your phase A voltage. Let me write it as VAN, or you can write it as VA also. Doesn't matter. VAN. Next, this is your phase B voltage. Let me write it as a phase B voltage. This is a VBN. And here it is a phase C voltage, right? Phase C voltage, VCN. How to draw these voltages? These are the balanced voltages now. So please try to understand. You can check VAN waveform. This angle, this axis is like, this is your omega t. Okay, this axis is a omega t. That is an angle. Okay. So now at omega t is equal to 0 degree, VAN is 0. At omega t is equal to pi by 2, VAN is peak value. At omega t is equal to pi, VAN is 0, right? So can I write VAN expression? So VAN is equal to Vm into sine of omega t. It is a sinusoidal, okay? At 0, it is a VAN 0. At omega t, pi by 2, VAN will be at a peak value. At omega t is equal to pi, this is a pi over, okay? At omega t is equal to pi, VAN is equal to 0, right? So like this. If VAN is this value, what about the VBN? Can we write? VBN is lagging to VAN by angle 120 degree. Okay, this angle is corresponding to 120 degree. So let me write it as Vm into sine of omega t minus 120 degree. Either you can write 120 or you can write 2 pi by 3 also. VCN is equal to Vm into sine of, either you can write omega t minus 240 degree, or you can write, which is equal to Vm into sine of omega t plus 120 degree. Both are having the same meaning, right? Both are the same. 120 degree. This is a VCN, right? Either this or this, you can say. So now you can check VAN, VBN, VCN. We're having the three voltages. Okay. These three voltages are phase displaced by 120 degree, means we're having the balanced supply. We're having the balanced supply. Let me indicate, yes. This is nothing but your, it is a pi by 6. Okay. This is a pi by 2. This indicates like a pi by 6, 2 pi by 6, 3 pi by 6, 4 pi by 6, 5 pi by 6. This is a 5 pi by 6. Okay. So this is like your pi. Okay. Next 6 pi by 6, 7 pi by 6. This is a pi. So therefore, yes, 5 pi by 6 pi. Next 7 pi by 6, 8 pi by 6, right? 9 pi by 6, 10 pi by 6. Okay. This is like your pi by 6 plus 120 degree. So it is 9 pi by 6. Okay, you can check it. This will be like your 2 pi. Okay, so 9 pi by 6, and this will be like your 13 pi by 6. Okay, so each interval is like a 30 degree. Each interval is like a 30 degree, means if this is pi by 6, this will be like your pi by 3. Okay, if this is pi by 3, this is a pi by 2. This is pi by 2 plus 30. So it is like a pi by 6, 2 pi by 6, 3 pi by 6, 4 pi by 6. Okay, so this is 4 pi by 6. Right, 4 pi by 6. Next, 5 pi by 6. This is 6 pi by 6 means pi. 6 pi by 6 means pi. Okay. After that, we will be having a 7 pi by 6. Okay, we will be having a 7 pi by 6, means this value. It is a 7 pi by 6. It means the different color. Yes, 7 pi by 6. Right. Next, 8 pi by 6, 9 pi by 6. This is 8 pi by 6. This is 9 pi by 6. This is 10 pi by 6. Peak value will be 11 pi by 6. 12 pi by 6 means a 2 pi complete na, and this is 13 pi by 6. So each interval is of 30 degree only. Each interval is of 30 degree only. Pi by 6 means 30 degree na, right? So this is our supply voltage. This is the supply voltage only, right? Next, you can check here. Yes, which diode is an uncontrolled switch na, right? And the diode, across which diode the maximum voltage will appear na, that respective diode will be in a conduction mode, right? So please try to understand. The voltage across diode D1 voltage across diode D1 is nothing but you can check anode of a diode D1 is connected to this point. Cathode of a diode, this is anode of a diode, no? This is a cathode of a diode. Cathode of a diode is connected at this point. Initially, it is like circuit will be at the rest position. All the three diodes will be in a off state. So if all the three diodes are in a off state initially, what is the current flowing through the load? Current flowing through the load will be 0. So current flowing through the load is 0 means voltage across load will be 0. So can I say that whatever the potential here, the same potential will appear here. Same potential will appear here, same potential here, same potential here. The meaning is the potential at this point, the potential at this point, initially I am saying, means when circuit is at the rest position, that is when all the three diodes will be in an off state, okay? Then the potential at this point is same as the potential at the neutral point. So neutral point potential is here, same appears, same potential, same potential, same potential, same potential. So here you can check when initially circuit is at the rest position. For the diode D1, the cathode potential is like a neutral potential. Anode potential is like a phase A potential. So can we say that the voltage across diode D1 is nothing but VAN? Yes or no? Initially, when all the three diodes are in a off state, voltage across diode D1 is nothing but a VAN. Similarly, you can check what about the voltage across diode D2? This is the anode of diode D2. This is the cathode of diode D2. At the cathode, which potential will be appearing? Whatever the potential here. And this potential is nothing but this potential we discussed, right? So here it is neutral point potential, means here it is also neutral point potential. What is the anode potential of the diode D2? It is a VBN. Whatever the potential here, it is a VBN. The same potential will appear here. So voltage across diode D2 is a VBN. Similarly, voltage across diode D3 is equal to VCN. Okay, so let me write here. Okay, initially, yes, when all three diodes, yes, are in a off state, okay, then voltage across diode D1 is equal to VD1 is nothing but your this voltage. Yes, VD1 is nothing but voltage across diode D1. VD2 is nothing but voltage across diode D2, and VD3 is voltage across diode D3. Okay, so VD1 is equal to VAN. VD2 is equal to VBN, and VD3 is equal to VCN. Now, yes, so if you check when initially all the three diodes are in a off state, okay, voltage across diode D1 is VAN, voltage across diode D2 is VBN, voltage across diode D3 is VCN. VAN is a phase voltage, VBN is a phase voltage, VCN is also phase voltage. Okay, now as I said, which diode will be in a conduction mode? That will be decided by the voltage VAN, VBN, VCN. Now you can check the VAN, VBN, VCN waveform. We're having this is VAN, this is VBN, this is VCN waveform, right? So you can check here from pi by 6 to pi, from pi by 6 to 5 pi by 6 means this instant to this instant. VAN will be at its maximum value. VAN will be greater compared to that of other two voltages now. So from pi by 6 to 5 pi by 6, VAN is the maximum compared to that of VBN, VCN. So can we say that as VAN is a maximum compared to that of other two voltages? So from pi by 6 to 5 pi by 6, definitely the diode across which the voltage VAN is appearing, that will be in a conduction mode. So which diode will be in a conduction mode? Diode D1, yes, will be in a conduction mode. Are you getting the point? Means from omega t is equal to pi by 6 to 5 pi by 6, VAN is a peak, VAN will be maximum. You can check during this interval. What is VBN? VBN is this value. This yellow one is nothing but VBN. So from pi by 6 to pi by 6, you can check VBN is like this. It is a less than that of VAN. Similarly, you can check the VCN also, pi by 6 to pi by 6. VCN is also lesser than VAN compared to the VAN. So that's why VAN will be maximum. So therefore, diode D1 will be in a conduction mode. From 5 pi by 6 to 9 pi by 6, from 5 pi by 6 to 9 pi by 6, VBN is maximum. So when VBN is maximum means definitely diode D2 should conduct now, because voltage across diode D2 is VBN, right? So therefore diode VBN should, that is diode D2 should conduct. From 9 pi by 6 to 13 pi by 6, diode D3 should conduct, because VCN is nothing but the voltage across diode D3. Okay, so here, yes, let us write during pi by 6 to 5 pi by 6, during omega t is equal to pi by 6 to 5 pi by 6. Yes, VAN is greater than VBN is greater than VCN. So therefore, voltage across diode D1 will be maximum compared to the VD2 and VD3. So therefore, VD1 is maximum compared to VD2 and VD3. VD2 and VD3. So therefore, diode D1 will conduct. Diode D1 will conduct, right? Because we have connected the diodes in this way. So which diode will be in a conduction mode, that will be decided by across which diode the maximum voltage is appearing, right? So therefore here diode D1 will be in a conduction mode. Diode D1 will be in a conduction mode, right? Next, now you can check. Yes, let us consider first from pi by 6 to 5 pi by 6. Diode D1 is in a conduction mode. So can we draw the waveform of V0 during that interval specifically? Let me draw the V0 waveform here. Omega t 0, and here it is a V0, right? So here it is a pi by 6. Pi by 6 to 5 pi by 6, right? Pi by 6 to 5 pi by 6. Now you can check from pi by 6 to 5 pi by 6 when diode D1 is in a conduction mode. That is when diode D1 conducts. How the current will flow? Current will flow from VAN, D1, load, and again back to the neutral point. Means in this loop the current will flow, yes or no, right? So now when diode D1 is in a conduction mode, can we apply KVL to this loop? It is a plus VAN minus VD1 minus V0 is equal to 0. But what is VD1? VD1 is 0 na? So if VD1 is 0, so can we say that plus VAN minus V0 is equal to 0? Means V0 is equal to VAN only, yes or no? So from pi by 6, from omega t is equal to pi by 6 to 5 pi by 6, in the output we will be getting only VAN. We will be getting only VAN. So let me draw this VAN waveform as it is will appear in the output. So we'll be getting this type of waveform in the output. This is your VAN. During this interval, which diode is in a conduction mode? Diode D1 is in a conduction mode, right? Now let us check what will happen at 5 pi by 6, okay, or after 5 pi by 6. You can check at 5 pi by 6. At 5 pi by 6, okay, it is like a VAN and VBN both are same, yes or no? VAN means this one red one and VBN is yellow one. After 5 pi by 6, VAN is lesser than that of VBN. So if VBN is greater than that of VAN, if VBN is greater than that of VAN, so it is like your diode D2 will start conduction. VBN is positive now, so it is plus here minus here. Diode D2 starts conduction, yes, at omega t is equal to 5 pi by 6. So once the diode D2 starts conduction at 5 pi by 6, what will happen to diode D1? Let us understand. Because initially diode D1 was in a conduction mode. At omega t is equal to 5 pi by 6, diode D2 voltage, or after omega t is equal to 5 pi by 6, diode D2 voltage will be greater than that of diode D1. Means it is like diode D2 will be more positive. Okay, more positive voltage will be appearing across diode D2. So D2 starts conducting immediately. Once D2 start conducting, what will happen to D1? Let us discuss. So you can check here. When D2 is in a conduction mode, this is a neutral point. Okay, so it is like suppose neutral point potential is a 0 volt. Okay, so therefore here potential is a VBN. When diode D2 is in a conduction mode, means here it is VBN, means definitely here it is VBN. This VBN will appear here. This VBN will appear here. Now you can check when diode D2 conducts na, to the anode of diode D1 the voltage is VAN. To the cathode of diode D2 is the voltage is VBN. So what is the voltage across diode D1? It is a VAN minus VBN. So you can check after 5 pi by 6, what is the difference? VAN minus VBN. Yes, after 5 pi by 6, you can check VAN is less than that of the VBN. So VAN is less than that of the VBN means what? Anode voltage is lesser than that of the cathode voltage. So for any diode, if anode voltage is less than the cathode voltage, what will happen? That respective diode will immediately turn off now, right? So once the D2 turns on, immediately your diode D1 will turn off. Are you getting the point, right? So once the D2 turns on, immediately diode D1 will turn off. So once D1, if suppose D1 is in the off state, so what will happen? Current will flow from VBN, D2, load, and again back to the neutral point. In this loop, the current is flowing now, right? So if the current is flowing into this loop, what is the V0? V0 is equal to VBN only, na? You can apply KVL plus VBN minus voltage across conducting diode D2 minus V0 is equal to 0. So V0 is equal to VBN only, right? So you can check from omega t is equal to pi by 6 to 9 pi by 6. From omega t is equal to pi by 6 to 9 pi by 6. Yes, it is like in the output we'll be getting the waveform of VBN. In the output we'll be getting a waveform of VBN, right? So VBN waveform is like this. Is this visible? Yellow color? Yes or no? The output will be getting the VBN waveform, right? VBN waveform. Yes, good. Okay. So here we'll be getting the VBN waveform. In the output, we are getting the VBN waveform, right? Means diode D2 is in a conduction mode, na? Whatever the shape of the VBN, same is appearing in the output voltage. This will continue till 9 pi by 6. At 9 pi by 6, you can check VCN and VBN both are same. And after 9 pi by 6, VBN is less than that of VCN. Na? VBN is less than that of VCN. Okay, so you can check. Yes. So after 9 pi by 6, VCN is having the maximum value compared to that of the other two, VN and VBN. So therefore, your diode D3 will turn on. Diode D3 starts conducting, yes, at omega t is equal to 9 pi by 6. Once D3 starts conducting, what will happen to diode D2? Let us understand. Okay, you can check. Once DT starts conducting means this is like minus here, plus here. This voltage 0 means this is the VCN voltage. So here it is voltage is VCN. This is VCN means definitely here it is VCN. Diode D3 is acting as a short circuit means here voltage is VCN. This is VCN means now here it is a VCN. Na? Definitely here it is also VCN. Definitely here it is also VCN will appear VCN. So you can check once D3 starts conduction, voltage at the cathode of diode D2 is VCN. Voltage at the anode of diode D2 is VBN. So anode voltage is VBN, cathode voltage is VCN. So you can check after 9 pi by 6, VBN is less than VCN. Na? So VBN is less than VCN means what? Cathode voltage is more compared to that of your anode voltage. So for diode D2, cathode voltage is maximum more compared to that of the anode voltage means what? Your diode D2 will turn off. Okay. So therefore only D3 conducts. So when D3 conducts in the output in the circuit, we will be having the current like VCN, D3 load and again back to the VCN. In this loop, the current will be flowing. Na? So what is the V0? V0 is equal to VCN. So in the output, we'll be getting the waveform which is same as that of the VCN. Okay. This will continue till 13 pi by 6. So this is a 13 pi by 6. Okay. So this will be like this. This is a VCN. Now you can check. This is like your 2 pi. Na? This instant is like 2 pi. Right? So this 2 pi to 13 pi by 6 means this 30 degree. Na? So 2 pi is like our again 0 angle. So this 30 degree indicates what? This 30 degree starting is 30 degree. So from 0 to pi by 6 again we'll be having whatever the waveform for 2 pi by from 2 pi to 13 pi by 6 na, means this waveform same will appear at the starting also means this type of waveform will be getting. Is this clear? Right? So 2 pi means one complete cycle of the supply is at this instant. This is a 2 pi. After 2 pi till 13 pi by 6 it is a 30 degree. So whatever the 2 pi to 13 pi by 6 waveform we're having in the output the same will appear at the starting also. Right? So it is like a pi by 6. This is like a 5 pi by 6. This is like your 9 pi by 6, 2 pi, and this is a 13 pi by 6. 13 pi by 6. Okay. So in the output, we are getting this type of waveform. We are getting this type of waveform. You can check each pulse is of 120 degree only. Corresponding to one input cycle. Now, one input cycle means 2 pi radius. So that's why it is a 3-phase, 3 pulse. That's why it is a 3-phase, 3 pulse. Okay. Let me indicate here. Yes. Yes. Here from here to here, diode D1 conducts. From here to here, diode D2 conducts. And from here till this instant, it is a diode D3. So same 2 pi to 13 pi by 6 means here also D3 will be in a conduction mode. Okay. So we'll be getting this type of waveform, right? So if this is a V0, what about the I0? Load is purely resistive now. So I0 will be in phase with V0 now, right? I0 will be in phase with the V0. So let me indicate I0. Yes, I0 will be like this. Let me just see. Right, actually the pulse width should be same, 120, 120, 120, right? So it is a pi by 6, 5 pi by 6, 9 pi by 6, and 13 pi by 6. After that again the same cycle repeats. Okay, same cycle repeats. So you can check, input is your AC but output is a DC na, only positive value you are having. Okay, but whether it is a flat DC, no, it is a pulsating DC. It is a pulsating DC, right? So this is for purely resistive load, right? Purely resistive load. Now can we write the V0 RMS expression? V0 RMS expression, yes, or V0 average first let us write, and after that we will discuss the V0 RMS, right? Yes, V0 average value of output voltage. So now you can check the waveform corresponding to 0 to 2 pi. How many pulses were having in the output? We're having 1 pulse, 2 pulse, and 3rd pulse here, and remaining part here. So we're having the 3 pulses now. So that's why it is a 3 by 2 pi. Please listen it carefully. It is a 3 by 2 pi I am writing because corresponding to 2 pi radian we're having the 3 pulses. Into integration, I will integrate only for the 1 pulse. Why it is? Because ultimately I have multiplied with 3 already. I am adding the instantaneous values over a 120 degree and I am multiplying that with 3, means ultimately it is like I have added instantaneous values of all the 3 intervals now, right? So it is like a integration from pi by 6 to 5 pi by 6, pi by 6 to 5 pi by 6. Yes, what is the value? You can check. It is a VAN from pi by 6 to 5 pi by 6. It is a VAN. What is a VAN? It is a Vm into sine of omega t, right? So let me write that Vm into sine of omega t into d omega t, right? Please try to understand this expression. Corresponding to 2 pi radian, we are having a 3 pulses. So that's why I have written 3 by 2 pi. And I have just added integration, means the addition of instantaneous values, okay, over only 1 cycle, that is the 1 pulse, that is pi by 6 to 5 pi by 6. So it is like what I have done, I have taken the integration over the 1 pulse, and to that I have multiplied with the 3 na. So it is like I have multiplied over I have added the instantaneous values of all the 3 pulses na. So 3 into this term is nothing but it is like a instantaneous values addition over of the 3 pulses, right? So that's why it is 3 by 2 pi. Either you can write in this way, or how you can write, it is like 1 by 2 pi, 1 by 2 pi into bracket we need to write pi by 6 to 5 pi by 6. This is the VAN, means this expression into d omega t, plus integration from 5 pi by 6 to 9 pi by 6. It is a VBN na. We need to put VBN, means this value, plus integration from 9 pi by 6 to 13 pi by 6. This is a VCN, is nothing but this value. Okay, either you can write 3 separate integrations and it is like 1 by 2 pi you can do, or whatever I have done, right? In this way also you can do, right? Because just now we discussed each pulse is of 120 degree only na, right? So that's why addition of instantaneous values of this pulse is equal to addition of instantaneous values of this pulse, which is equal to same here, right? So that's why we're multiplying with the 3. Okay, so 3 by 2 pi. Next, can we simplify it? Yes, it is equal to 3 into Vm divided by 2 pi. 3 into Vm divided by 2 pi. Yes, what is the integration of sine? It is a minus cos of omega t. Limit pi by 6 to 5 pi by 6. Okay, so this can be written as 3 into Vm divided by 2 pi into minus cos of omega t. Okay, put the limit. It is a cos of pi by 6 minus cos of 5 pi by 6. So if you check, it is equal to 3 Vm divided by 2 pi into cos pi by 6 minus cos 5 pi by 6. Okay, it is 0.866, that is a root 3 by 2 minus cos of 5 pi by 6, that is a 150 degree. It is a minus 0.866. So this minus, so plus root 3 by 2. Okay, so if you check, it is equal to V0 average. Therefore, V0 average is equal to, we can write 3 root 3 by 2. Root 3 by 2 means again it is a root 3 only, na, right? So 3 root 3 Vm by 2 pi. 3 root 3 into Vm divided by 2 pi. Further, I can write it as root 3 into Vm. You can check the transformer secondary is a star connected. And for 3-phase half-wave rectifier, we require a star connection only. Why? Because specifically here we require a 4-wire supply, na, or 4-wire connection. And 4-wire connection is possible only in a star connection. Whether your delta connection gives the 4-wire connection, no, right? So we require a 4-wire, means 1, 2, 3, and here through load 4-wire having. Okay, so that's why transformer secondary should be connected in star. Okay, so for the star connection, yes, what is the relation between line voltage and phase voltage? Line voltage is equal to root 3 into phase voltage, na, right? So let me write it as, yes, here it is root 3 into Vm means what? Yes, it is a 3 into VML divided by 2 pi. What is VML? Peak value of line voltage, where VML is the peak line voltage. Peak line voltage. And what is Vm? You can check this Vm, na? Vm means we have written here. This is Vm, this is Vm, this is Vm. What is this Vm indicates? Peak phase voltage, na? Because VAN, VBN, VCN, these are the phase voltages. So Vm is nothing but peak value of phase voltage. Okay, so it is a peak phase voltage. Peak phase voltage. Yes or no? Peak phase voltage, right? So this is your V0 average. V0 average. Similarly, we can write I0 average. I0 average is V0 average by R, na, resistive load. Okay, so I0 average is equal to V0 average divided by R. Can we write the V0 RMS value of output voltage? Again, same 3 by 2 pi integration from pi by 6 to 5 pi by 6. Pi by 6 to 5 pi by 6. Yes, it is a Vm square into sine square of omega t into d omega t to the power 1 by 2. Square root of mean of squared value. So we can write it as a root 3 into Vm divided by root 2 pi into integration from pi by 6 to 5 pi by 6. Sin square of omega t can be replaced with 1 minus cos of 2 omega t divided by 2, na, into d omega t to the power 1 by 2, right? So these two also we can take outside. So it is like root 3 Vm divided by 2 root pi. Root 3 Vm divided by 2 root pi into, it is like a integration of 1. I have taken these two outside. So integration of 1 is the omega t. Let me write it as omega t minus integration of cos is sine of 2 omega t divided by 2, right? Sine of 2 omega t divided by 2. Limit pi by 6 to 5 pi by 6 to the power 1 by 2. Further, we can put the limit, right? So therefore, V0 RMS. Yes, therefore, V0 RMS. We can write it as root 3 Vm divided by 2 root pi. Root 3 Vm divided by 2 root pi into 5 pi by 6 minus pi by 6. That is a 4 pi by 6. Okay. So 4 pi by 6 means it is a 2 pi by 3, na? Right? Next, put the value here. Minus sine of 1 by 2 we can take outside. Okay. Minus sine of, or minus 1 by 2 into sine of it is a 2 omega t na, so 2 into pi by 6 means 10 pi by 6. Okay, 10 pi by 6, so it is a 5 pi by 3 na. This is one thing, plus I'm writing here 1 by 2 into sine of, yes, put this limit pi by 6, so it is a 2 pi by 6, that is a pi by 3, sine of pi by 3. So if you check, it is root 3 into Vm divided by 2 root pi into 2 pi by 3, yes, minus sine pi into pi by 3, sine 300 na? So it is a minus 0.86. It is this minus and this minus, it will become plus. Okay, so it is like 1 by 2 into root 3 by 2 plus here sine, yes, same, it is again root 3 by 2, so 1 by 2 into root 3 by 2. So we can write it as root 3 into Vm divided by 2 root pi, right, into 2 pi by 3 plus this will be your root 3 by 2, 1 by 2 root 3 by 2 plus 1 by 2 root 3 by 2 plus 1 by 2 root 3 by 2. So it is like root 3 by 2 na, root 3 by 2, right? So this is the expression for V0 RMS. Or further what we can do, we can add these two. Okay, either keep it as it is or you can add. Sorry, this is power 1 by 2 na. Yes, 1 by 2 should be there. Here it is 1 by 2. Here it is 1 by 2. Correct. This is the V0 RMS, right? Further, what we can do, I can replace this root 3 into Vm with a VML. Okay, with a VML. Okay, or keep it as it is. Doesn't matter. Please keep it in mind. Vm means peak value of phase voltage. VML is peak value of line voltage. Okay, so this is V0 RMS. Next, I0 RMS. I0 RMS is equal to V0 RMS divided by R. V0 RMS divided by R, right? Next, what is the load power? Can we find load power P0 average? It is equal to V0 RMS into I0 RMS. Yes or no? Right? Resistive load. So RMS voltage into RMS current. Be careful. Output side is a DC. Generally, students think that it is a 3-phase na. So generally they multiply it with a 3. No, this is a blunder mistake. Okay, so please keep it in mind. Output is a DC na, input is AC, but output is a DC. So that's why it is a V0 RMS into I0 RMS, right? Next, what is the conduction time of each diode? Conduction time of each diode. Each diode is in the on state for 120 degree na. So conduction time is angle divided by, that is 2 pi by 3 divided by omega na, 2 pi by 3 by omega. So it is 2 pi by 3 omega. 2 pi by 3 omega. Yes, what is the PIV rating? Come on. PIV rating of each diode. Yes, can anyone? What is the PIV rating of each diode? Yes, here it is a circuitry. Please check what is the PIV rating of each diode. At a time, one diode will be in a conduction mode na. So suppose here D3 is in a conduction mode. Suppose D3 is in a conduction mode. When D3 is in a conduction mode, here it is VCN, here it is VCN. D1, D2 will be in a off state na. So what is the voltage across at the cathode of diode D2? It is a VCN. Voltage at the anode of diode D2, it is a VBN. So what is the voltage across diode D2? It is a VBN minus VCN na. So VBN minus VCN is a line voltage or phase voltage? VBN minus VCN is a line voltage or phase voltage? It is a line voltage na. So what is the peak value of that line voltage? It is a VML na. Yes or no, right? So please try to understand. PIV rating is equal to VML. PIV rating is equal to VML, right? So each diode is equal to VML. VML is nothing but maximum value of line voltage. Because when at a time one diode is in a conduction mode, then the remaining two diodes will be in off state. Okay, and the voltage that will be appearing across remaining two diodes is nothing but your line voltage. Okay, difference between two phase voltages means the line voltage. Okay, so that's why the peak inverse voltage is nothing but your maximum value of line voltage. Maximum value of line voltage, right? So VML. Next, can we draw the waveform of ID1? Can we draw the waveform of ID1? Diode D1 current, yes. Diode D1 is in a on state from omega t is equal to, we have written pi by 6 to 5 pi by 6. D1 is in on state na. So only during this interval the current will be flowing through the diode D1, and that current is nothing but your load current na. So this type of waveform will be getting in the ID1. Okay, only from pi by 6 to 5 pi by 6. Okay, so ID1, that is non-zero from pi by 6 to 5 pi by 6. Okay, and remaining till 2 pi it will be 0 only. So let me draw this waveform. The waveform will be like this. Only during this interval we will be having the waveform. ID1 will be non-zero. Okay, what is this value? This value is like your load voltage, right, divided by resistance na. Load voltage divided by resistance. Okay, and what is the load voltage during this interval? It is a VAN na, right? So it is a VAN divided by resistance. VAN by resistance. Is this clear? And for this interval and from here to here it will be 0. It will be 0, right? Diode D1 is in on state only from pi by 6 to 5 pi by 6. So that's why current flowing through diode D1 is non-zero only during this interval. Yes or no, right? And you can check when D1 conducts, load current is equal to your ID1 na? Same current. Or can we say that this ID1 is nothing but again phase A current also? Can I indicate this as a phase A current IA? Whether ID1 and IA both will be same or different? Whether ID1 and IA both will be same or different? Phase A means your supply current, right? ID1 and IA both will be same na. When diode D1 is in on state, then and only then IA will be non-zero. When diode D1 off, your IA will be 0. So IA and ID1 both will be same na. IA and ID1 both will be same only, right? So both will be same. So can we write it as, you can write it as ID1 or you can write it as IA also. IA means what? Phase A current. IA means the phase A current, right? Next. So now can we write the ID1 average? Yes, ID1 average, which is equal to IA average. Yes, is equal to, we can write it as 1 by 2 pi integration from pi by 6 to 5 pi by 6. What is this value? VAN by R. What is VAN expression? Vm into sine of omega t, right? So it is a Vm into sine of omega t divided by R into d omega t as it is, right? This divided by R as it is. So we can write it as Vm upon 2 pi R into integration of sine is minus cos of omega t, limit pi by 6 to 5 pi by 6. Okay, so therefore we can write ID1 average, which is equal to I0 average. Yes, it is equal to Vm by 2 pi R into, yes, it is a cos pi by 6 minus cos of pi by 6 minus cos of 5 pi by 6. You can check this bracket. It is a Vm by 2 pi R into this is root 3 by 2 and this one is also root 3 by 2, right? Yes. So this will be like a root 3. So it is equal to your root 3 into Vm, means VML upon 2 pi R. VML upon 2 pi R. This is your ID1 average, which is equal to I0 average. Further, you can check what is the, no, this is IA average, not I0. It is corrected, IA average. Here I have written IA average, right? So IA average. VML upon 2 pi R, right? Root 3 into Vm means what? VML, na? What is your I0 average? If you check the I0 average expression, I0 average, we have written V0 average by R. And what is V0 average? 3 VML by 2 pi, na? So can I say that I0 average is 3 VML by 2 pi R? This term divided by R, na? Means I0 average. So I0 average is 3 VML by 2 pi R. And your ID1 average is VML by 2 pi R. So can I write it as, which is equal to I0 average divided by 3? Yes or no, right? because each diode is in a conduction mode for 120 degree, right? So diode current average value is equal to your that respective phase current average value is equal to load current average value divided by 3. That is 1/3 into I0 average, right? So this is the diode current, right? Next, so this is about for purely resistive load. Okay, purely resistive load. Now let us discuss for REL load. Okay, let us discuss for REL load, right? REL load and constant load current, right? REL load and constant load current. Because generally in three phase, if the load is REL, yes, there is a high possibility of getting the constant load current, right? How we'll discuss. So next for REL load, three phase, three pulse, uncontrolled rectifier. With RL load. Right. Same circuit diagram. I am drawing the secondary side only. Yes, this is your VAN. This is a neutral point. This is the VBN. This is the VCN, right? Diodes are D1, D2, and D3. Okay, so R, L, V0, and I0, right? I0. Suppose I0 is a constant or highly inductive. So, yes, the waveforms. Right. So supply voltage waveform, it will be same as that of the previous one. In that we are having a voltages like VAN, VBN, and here it is a VCN. This is like your pi by 6. This is 2 pi by 6, 3 pi by 6, 4 pi by 6, 5 pi by 6, right? This is 6 pi by 6 means a pi radian. 7 pi by 6, 8 pi by 6, 9 pi by 6, 10 pi by 6, 11 pi by 6, 12 pi by 6, that is the 2 pi, and this is a 13 pi by 6, right? This is a 2 pi, right? This is a 2 pi here. Next, V0 waveform, how it will be? And the I0 waveform. Right? So as we discussed, yes. Okay, so now you can check during pi by 6 to 5 pi by 6. VAN is a peak value now. So therefore, what will happen in the circuit? If you check here in this circuit, your diode D1 will be in a conduction mode from pi by 6 to 5 pi by 6. Current will flow from VAN, D1, load, and again back to the neutral point, right? So it is like inductor go on storing the energy. Inductor stores energy, right? But after this point, what will happen? Yes, after 5 pi by 6, when VBN will be at a peak value now, means when diode D2 conducts, then it is like our inductor will be releasing the energy through this loop only. Through diode D2, inductor go on releasing the energy. So even though your load is RL load, right, it doesn't change your load voltage. Are you getting the point? Because when D1 is in a conduction mode, load inductor is just storing the energy. Suppose at 5 pi by 6, D2 starts conduction, D1 will turn off. Okay. Then in this same loop, we are having the inductor, okay, is having the path to release the energy, na? Right? So that's why inductor will continue releasing the energy, and again after some time it will be charging. After some time it will go on charging, and that is storing the energy. Okay. So please try to understand. Yes, from omega t is equal to pi by 6 to 5 pi by 6, diode D1 is in a conduction mode, right? Next, from 5 pi by 6 to 9 pi by 6, same diode D2 conducts. When D2 conducts, D1 will turn off due to the reverse voltage. How we have discussed it. Okay. Similarly, from 9 pi by 6 to 13 pi by 6, the diode D3 starts conduction. And always what is happening here, the inductor is having the path to release the energy. What is the tendency of the inductor? Inductor will try to oppose the change in the current, na? Means inductor will try to maintain the current in the downward direction only. So when D1 conducts, suppose current is in the downward direction, when D1 turns off, our inductor will continue releasing the energy through diode D2 only. Because as soon as D1 turns off, we are having the VBN will be the maximum, the VBN will be maximum compared to that of VN, VCN, means our diode D2 will be immediately forward bias mode. So that's why our inductor will continue releasing the energy through diode D2. So that's why here, even though the inductor is releasing the energy, our output voltage will not change. Output voltage will remain same only. Similarly, for D2, for some period, inductor releases energy. After that, again, it will store the energy, right? Again, at this instant, if you check 9 pi by 6, D2 turns off, again, D3 will turn on immediately. So inductor will go on releasing the energy through diode D3. Inductor will release the energy through diode D3. Okay. And now you can check during these respective intervals, yes, what is happening here? VIN is positive during this interval, pi by 6 to 5 pi by 6, right? So when VIN positive, current allowed through the diode is in this direction only. And inductor is also, yes, inductor is also required to continue to maintain the current in the same direction only, na? Right? So it is unlike your half wave rectifier. In the half wave rectifier, what was the single phase half wave rectifier? What was the condition? There we had only one diode, na? There we had only one diode or one thyristor actually in that case. Okay. If you recall the diode, if you recall the single phase half wave diode rectifier, that is the uncontrolled rectifier. Okay. In that case, what was happening? Yes, it is like a waveform. If you recall the V0 waveform, from 0 to pi, it was a positive only. Pi to 2 pi also, it was a positive. Yes or no? Right? So that type of thing we were having. Okay. But here it is a different thing. Right? So single phase half wave uncontrolled rectifier, that is a one diode. Suppose if you are having, sorry, in that case, actually it was like from omega t is equal to 0 to pi, voltage was positive. And after pi till beta, it was negative. Okay, after pi till beta, it was negative. Okay, why negative? Because inductor was releasing the energy through the same diode. But here inductor did not to release the energy through the same diode, because once this diode is in an off state, immediately this diode will turn on. Na? So inductor will be getting the path to release the energy through the same this diode. Okay, so that's why it will not affect on the output voltage. Okay, so you can check the output voltage waveform. It will be like this only. Let me use, yes, this color. This type of waveform will be getting. Right? So this is like pi by 6, 5 pi by 6, 9 pi by 6, and here it is a 13 pi by 6. Okay. So what is the I0? I0 will be your constant current. This is a constant current I0, right? Next. Anonymous attendee, will you please unmute yourself? You are speaking in messages a lot things, right? Lot of things you are speaking. Please mute once. I want to talk with you. Okay. ठीक है. Right? He's saying that, sir, tomorrow we are having the 7 hours, so please stop. Okay. Okay. No, we'll complete the control rectifier also today. Okay. Probably purely resistive load. Okay. Yes. So this is your I0, that is a constant current, right? So now here, if you check in the output, we are getting the pulse as a VAN. This is a VBN, and here it is a VCN. So in this, again, what is the V0 average? Whether it will be same as that of the previous case or different? Same as that of the previous case only, na? Right? So no need to derive here, right? So let me write here only thing. V0 average is equal to 3 by 2 pi integration from pi by 6 to 5 pi by 6. Pi by 6 to 5 pi by 6. It is Vm into sine of omega t. That is VAN is there, na? And what is the expression of VAN? Yes, it is a Vm sine omega t, right? So no need to derive it, keep it as it is. What is I0 average? Capital I0. I0 average is equal to capital I0, right? V0 RMS is equal to 3 by 2 pi integration from pi by 6 to 5 pi by 6. It is like a Vm square into sine square of omega t into d omega t, right? To the power 1 by 2, no? To the power 1 by 2, right? Same expression we have already derived. What is I0 RMS? Whether it will be same as that of your I0 average or different. I0 is a constant current, na? So I0 RMS is a I0 average, which is equal to capital I0, which is equal to capital I0, right? Next, now, what is load power T0 average? Can we write I0 average is a constant, na? That is a constant I0. So can we write P0 average is equal to V0 average into I0, right? So, right? So this is about the RL load. Conduction time of each diode, it is again same. Okay. PIV rating of each diode, again it is the same, right? Because circuit operation is same, right? Now let us discuss a single phase, sorry, 3-phase half wave controlled rectifier. Okay, 3-phase half wave controlled rectifier. So what will happen if we replace the diodes with the thyristors? Let us discuss. Okay, so yes, 3-phase half wave controlled means again 3-phase 3 pulse only. Yeah, 3-phase 3 pulse only. 3-phase half wave controlled rectifier, or it is also known as a 3-phase 3 pulse rectifier. 3-phase 3 pulse rectifier. Let us first discuss with the R load. Let us first discuss with the R load. Right? Yes, we are having a transformer. Right, primary of the transformer may be connected in star or delta. Right, I am going to draw the secondary side circuit only here. Yes, circuit will be like this. Same as that of the previous case. The only thing is we need to replace the diodes with a thyristor, right? Just a minute. Suppose load is a purely resistive load, right? Okay, so this is thyristor T1, T2, T3, R. This voltage is a VAN, neutral point, VBN, and VCN, right? Suppose this current is a IT1, This current is like a IA, voltage V0, and current is a I0. Right? So now, yes, again here at a time only one thyristor will be in a conduction mode, just like a diode here. But when at a time only one thyristor is in a conduction mode, the voltage across load will be equal to your phase voltage, right? So that's why in the supply system here we are having a phase voltage waveform. Okay, in a supply voltage we are having a phase voltage waveform, right? So three phase voltages we are having, same as that of your diode rectifier case. Okay, so voltages are, this is VAN, this is VBN, this is a VCN. Let me mark here. This is your pi by 6, 2 pi by 6, 3 pi by 6, that is a pi, 4 pi by 6, and here it is a 5 pi by 6, 6 pi by 6, 7 pi by 6, 8 pi by 6, 9 pi by 6. Okay, 10 pi by 6, 11 pi by 6, 12 pi by 6, and 13 pi by 6, right? 13 pi by 6. So this is 13 pi by 6, right? So this indicates here it is a 2 pi actually. This is a 2 pi, and 2 pi plus 30 degree means 13 pi by 6. Okay, 13 pi by 6. Now, how is the waveform of V0? Let us discuss V0 and I0 waveform, right? Right, so okay. Okay, so here V0 voltage across load, I0 is the current flowing through the load, right? So same supply voltage waveform VAN, VBN, and VCN. So it is like initially all the three thyristors will be in a off state. Okay, so instead of diode D1, now we are having a thyristor T1. Instead of diode D2, we are having a thyristor T2. Instead of diode D3, now we are having a thyristor T3. Okay, now here you can check diode circuit and thyristor circuit. What is the difference? For a thyristor, alpha equal to 0 is nothing but a diode circuit, na? Yes or no? Right? If we keep alpha equal to 0 degree for thyristor, then it is like it will be a diode circuit, na? So now can we say that here, if you check previous circuit at pi by 6, okay, from pi by 6 to 5 pi by 6, it was like a diode D1 was in a conduction mode, na? Because it is like diode D1 was in a forward bias mode. Okay, so can I say that this point is nothing but alpha equal to 0 degree for thyristor T1? Please try to understand this point. This is very important. Why I'm saying this point is nothing but alpha equal to 0 degree for thyristor T1. The meaning is after this point only our thyristor T1 will be in a forward bias mode. Because you can check in a continuous cycle. In a continuous cycle, if you check, yes, in the output will be having VAN, VBN, and some portion of the VCN. Na? So before VAN, we'll be having a VCN. So if we want the VCN in the output voltage, definitely thyristor T3 should be in a conduction mode. Na? So when T3 is in a conduction mode means what? Here voltage is, you can check, when T3 is in a conduction mode, sorry, this is VBN, this is VCN. Na? This is the VBN, here it is a VCN. Okay. So when T3 is in a conduction mode means here it is a VCN and here it is also VCN. If this is VCN, here it is VCN, here it is VCN. At this instant, the voltage is VAN. So now you can check in the continuous cycle. I am saying in the continuous cycle, before VAN, which pulse will be present? Before VAN, the VCN pulse will be present. So in order to get the VCN in the output, thyristor T3, yes, should be in the on state. So when T3 is in on state, here it is VCN, here it is VCN, here it is VCN. So what is the voltage across thyristor T1? VAN minus VCN. Na? So VAN minus VCN, that is the voltage across thyristor T1. Anode voltage is VAN, cathode voltage is VCN. So anode voltage is VAN, cathode voltage is VCN. You can check. VCN means this blue line. VAN is nothing but this red curve. Okay, red line. So you can check before pi by 6. Before pi by 6, VCN is greater than VAN. Okay. So if VCN is greater than VAN, the meaning is cathode voltage of thyristor T1 is greater than that of the anode voltage. Na? So whether, my question is, during 0 to pi by 6, in a continuous conduction, I am saying in a continuous conduction, whether our thyristor T1 will be in a forward bias mode? No. Thyristor T1 will be in a forward bias mode only when your VAN will be greater than VCN, and VAN will be greater than VCN only after pi by 6. So that's why I'm saying that at omega t is equal to pi by 6, it indicates alpha equal to 0 degree for T1. You can check for the diode rectifier also. The diode D1 started conduction at pi by 6, na? Right? And diode rectifier and thyristor rectifier, what is the difference? Thyristor rectifier alpha equal to 0 degree means your diode rectifier output voltage if you compare, right? So this is your alpha equal to 0 degree for thyristor T1, right? Means after this instant only we can apply the gate pulse to thyristor T1. If I apply the gate pulse to thyristor T1 before pi by 6, our thyristor T1 will not turn on at all. Why? Because before pi by 6, there was a thyristor T3. Okay, that thyristor was in a conduction mode. When T3 was in a conduction mode, voltage at the cathode of thyristor T1 is equal to VCN. Voltage at the anode of thyristor T1 is equal to VAN. So voltage across thyristor T1 is VAN minus VCN. So unless and until your VAN becomes greater than the VCN, we cannot apply our gate pulse to thyristor T1, right? So it is like alpha equal to 0 means for thyristor T1, we are going to measure the firing angle alpha after this instant, that is after omega t is equal to pi by 6. So let me write for thyristor T1, alpha equal to 0 degree means what? Omega t is equal to pi by 6. Omega t is equal to pi by 6, right? Next, you can check. So from T1 till 5 pi by 6, from T1 till 5 pi by 6, VAN will be maximum, na? Now you can check after 5 by, after means at pi by 6, suppose we applied the gate pulse to T1, na? So it is like a T1 will be starting conducting. So when T1 starts conduction, here it is VAN means here it is VAN. At this instant, the voltage will be VAN. That is the, at the cathode of thyristor T2, voltage will be VAN. Here it is also voltage VAN. And definitely when T1 starts conduction, your T3 will turn off. Okay. How will turn off? We'll discuss it while discussing the circuit operation. Okay. Now we are only discussing about the alpha equal to 0 degree for respect to thyristor. Okay. So when T1 is in a conduction mode, then here voltage is VAN, here voltage is like a VBN. Na? So unless and until your VBN becomes greater than VAN, yes, your thyristor T2 will not switch into the forward bias mode. So you can check VB after this instant, VBN is greater than VAN. So can I say that this point is nothing but alpha equal to 0 degree for thyristor T2? Similarly, you can check if this is alpha equal to 0 for T2. Similarly, you can check this is nothing but your alpha equal to 0 degree for thyristor T3. Okay, so please try to understand. Here alpha equal to 0 degree for thyristor T2. For thyristor T2, alpha equal to 0 degree means omega t is equal to 5 pi by 6. And for thyristor T3, alpha equal to 0 degree means omega t is equal to 9 pi by 6. 9 pi by 6, right? Means we are going to measure the alpha value, that is the firing angle for respect to thyristors. Okay. After these instants, okay, after pi by 6 for thyristor T1, after 5 pi by 6 for thyristor T2, after 9 pi by 6 for thyristor T3. Okay. Now suppose, yes, in this case or in this circuit analysis, we are having the two modes. One is if alpha is less than 30 degree, what will happen? And if alpha is greater than 30 degree, what will happen? Okay. So let us first discuss for alpha equal to alpha less than 30 degree. Okay, alpha less than 30 degree. Yes. So let me write here for alpha less than 30 degree. Alpha less than 30 degree means it is greater than 0, but it is less than 30 degree. Means the meaning is, suppose this omega t pi by 6 means we are applying the gate pulse to thyristor T1. Okay. sorry, omega t pi by 6 means alpha equal to 0 degree for T1 na. So this is pi by 6 and this is like your 2 pi by 6 na, that is pi by 3. This instant is pi by 3 na. Here from different angle difference between this point and this point is a 30 degree. Okay. And here we are discussing the alpha less than 30 degree. The meaning is we need to fire the thyristor T1 in between these 2 points, in between these 2 points. Okay. So let me take the, yes, projection here. This is one thing. This is 5 pi by 6. So this point is like your 5 pi by 6 plus 30 degree. That is a pi radian. 6 pi by 6 means what? It is a pi. This is 9 pi by 6. 9 pi by 6 plus 30 means 10 pi by 6. 10 pi by 6 is nothing but your 5 pi by 3. 5 pi by 3 point. Please try to understand. This is your alpha equal to 0 degree point. This point is nothing but after alpha 0, if we add 30 degree means this point will be reaching. Okay. So now we are interested in maintaining alpha less than 30 degree. So suppose if we select alpha is equal to 15 degree, alpha equal to 15 degree. The meaning is alpha 15 degree means we are supposed to apply the gate pulse to thyristor T1 at this instant, na? At this instant, right? So this instant is nothing but this point. Okay, here I am applying the gate pulse to thyristor T1. Next, alpha is equal to 15 degree for thyristor T2 means I need to apply the gate pulse to, yes, thyristor T2 here. So here I need to apply the gate pulse to thyristor T2. Similarly, alpha equal to 15 degree for thyristor T3 means I need to apply the gate pulse here. So you can check this instant indicates your alpha for T1 na. This point to this point, this angle is nothing but alpha for T1. What this point indicates? This point indicates your alpha for T2. This point indicates, or this difference indicates your alpha for thyristor T3. Are you getting the point? This is your pi by 6 and this point is nothing but pi by 6 plus alpha. This is like your 5 pi by 6 and this point is nothing but 5 pi by 6 plus alpha. This is a 9 pi by 6. This point is nothing but 9 pi by 6 plus alpha. Okay. Means now we are maintaining alpha less than 30 degree. Alpha less than 30 degree. The meaning is we are supposed to fire the thyristor T1 at this instant. We are supposed to fire the thyristor T2 at this instant. We are supposed to fire thyristor T3 at this instant. Okay. Now let us discuss. Suppose I am firing the thyristor T1 at this instant. I am firing the thyristor T1 at this instant. Okay. Yes. Means at this point I am firing the thyristor T1. Before T1, which thyristor will be in a conduction mode? Before T1, thyristor T3 will be in a conduction mode. Na? So when the T3 is in a conduction mode, how the current will be flowing? Current will be flowing from VCN, T3 load and again back to the VCN. In this loop, the current will be flowing. Na? So what is the V0? V0 is equal to VCN, right? V0 is equal to VCN means in the output, we'll be getting the VCN waveform. In the output, we'll be getting the VCN waveform. So you can check VCN waveform is this one, that is the blue one. So from 0 till this instant, this instant we'll be getting in the output, that is the VCN. So how is the VCN waveform? You can check from 0 till this instant in the output, it is a VCN. This type of waveform will be getting. Next, whether it will be reaching the 0 value, no, you can check corresponding to this point, VCN is here, na? This is a non-zero value, right? So in the output, we'll be getting a VCN. At this instant, we are triggering the thyristor T1. Okay. So if we are triggering the thyristor T1 at this point, then what will happen? Your thyristor T1 will turn on. Once the T1 turns on, or before that, you can check, we are triggering the thyristor T1 at this instant. Okay. Now, before this T3 was in a conduction mode, when T3 was in a conduction mode means here it is VCN, here it is VCN only, na? When T3 conducts, what is the voltage appearing here? VCN. Here VCN, because T3 is acting as a short circuit, na? So VCN, here it is VCN, here it is VCN. So what is the voltage that will be appearing across T1? VAN minus VCN, na? So you can check at the instant of firing, at the instant of triggering of a thyristor T1, whether VAN is greater than VCN or VAN is less than VCN. You can check. At this instant, actually, we are firing at this instant, right? So this instant, we are firing the thyristor T1. That yes, this red one. So at this instant, when we are firing the thyristor T1, you can check corresponding to this point, VCN is here and VAN is here. Na? So whether VAN is greater than VCN or less than VCN, VAN is greater than VCN. If VAN is greater than VCN, so can we say that thyristor T1 will be in a forward bias mode? Yes. So thyristor T1 is in a forward bias mode and we are applying the gate pulse, means what? Definitely our thyristor T1 will turn on immediately. Once the T1 starts conduction, what is the voltage that will be appearing here? You can check. Once the T1 starts conduction, means T1 is acting as a short circuit. Here it is VAN, means here it is VAN. Definitely here it is VAN. Definitely here it is VAN. So what will happen to T3? Once the T1 starts conduction, what will happen to T3? Voltage at the cathode of thyristor T3 is VAN. Voltage at the anode of thyristor T3 is VCN. So you can check the VCN and VAN voltages at the instant of triggering of thyristor T3. So at the instant of triggering of thyristor T3, means at this instant, VAN is greater than VCN. Na? So if VAN is greater than VCN, means what? Cathode voltage of thyristor T3 is greater than that of the anode voltage, means thyristor T3 will turn off immediately. Thyristor T3 will turn off immediately. Means only thyristor T1 will start conducting. So when T1 starts conduction, current will flow from VAN, T1, load, and again back to the VAN. In the output, we'll be getting it is a VAN. Okay, so we can check. In the output, we'll be getting the VAN. Means at this instant, T1 is triggered. Before that, output voltage was like a VCN, means till VCN, the point was like this. So once T1 starts conduction, output voltage will be VAN. So you can check at this instant, VCN is this one, VAN is this one. So here, there will be a sudden increase in the output voltage. There will be a sudden increase in the output voltage from VCN to VAN. And after that, the output voltage will be continued till this instant. That is till we fire the thyristor T2. Which the output will be getting this type of waveform. This is a VAN. Yes or no? Right? Now, at this instant, we are firing the thyristor T2. Na? At this instant, we are firing the thyristor T2. Right? So this instant is nothing but this instant again here. Okay. So at this instant, let me use the color. Yes, at this instant, actually, we are firing the thyristor T2. Okay. So till this instant in the output, it was a VAN, na? Right? So when VAN was in a conduction mode, when T1 was in a conduction mode, at the cathode of the thyristor T2, which voltage was there? VAN. Anode voltage is VBN. Okay, so you can check at the instant of triggering of thyristor T2 whether anode voltage is greater than that of cathode voltage or it is a less than that of cathode voltage. Check the VBN and VAN values. Okay, so at this instant we are triggering, means at this instant we are triggering. You check you can check VAN is this point, VBN is this point. So VBN is greater than VAN. Na? VBN is greater than VAN means anode voltage is greater than the cathode voltage. If anode voltage is greater than the cathode voltage, means thyristor T2 is in a forward bias mode. So T2 is in a forward bias mode and we are applying the gate pulse now. So definitely our thyristor T2 will turn on. So when T2 turns on, what will happen to T1? When T2 turns on, what will happen to T1? Once T2 turns on, this voltage will be like a VBN, means it is acting as short circuit now. So it is VBN, here it is VBN, here it is VBN. So now you can check thyristor T1. Cathode voltage is VBN, anode voltage is VAN. So at the instant of turning on, triggering of thyristor T2, please check whether VAN is less than VBN or greater than VBN. Okay, so corresponding to this instant, you can check VBN is greater than VAN. Yellow line is VBN, red one is a VAN. VBN is greater than VAN means what? The thyristor T1 will be in a reverse bias mode. So thyristor T1 will turn off. So only thyristor that will be in a conduction mode is a thyristor T2. So how the current will flow? Current will flow from VBN, T2, load, neutral, and again back to the VBN. So what is the V0? V0 is equal to VBN. We'll be getting V0 is equal to VBN, right? So in the output, we'll be getting a VBN, right? So let me indicate it with, yes. It is a VBN. The output, it will be VBN. This is a VBN, right? VBN, we are getting. Next, this will continue till we fire the thyristor T3. At this instant, we are firing the thyristor T3. So when T3 turns on, immediately your thyristor T2 will turn off. Okay, so same, when T3 turns off, T3 turns on, T2 will turn off. Okay, and in the output we'll be getting the VCN waveform. So VCN waveform is like this. So this type of waveform will be getting in the output. Okay, we'll be getting in the output. This is the VCN. So now you can compare. If you compare this waveform with the alpha equal to 0, that is the diode rectifier. In the diode rectifier, it was like from pi by 6 to 5 pi by 6, we are having this type of waveform. Means increase and slowly decrease. And again, from the same point, it was increasing now. But here it is, you can check, it is a decreasing and it is a sudden increase. Next, same as that of the VAN, decreases, sudden increases. Decreases, sudden increases. Means sudden increase is possible here in this case, right? So that's why V0 is like this we are getting. Okay, this is for alpha less than 30 degree. Alpha less than 30 degree. What about the I0 here? What about the I0? Load is purely resistive. So I0 will be in phase, na? I0 will be in phase. So your I0 waveform will be like this. From here to here, it will be in phase with VCN. Next, same waveform. Same waveform. The same waveform. Okay, this is your I0. Okay, I0. Right? This is true only when alpha is equal to alpha less than 30 degree. My question is, suppose if alpha is equal to 30 degree, what will happen? If alpha is equal to 30 degree, what will happen? Come on. Suppose if alpha is equal to 30 degree, what will happen? Alpha equal to 30 degree. You can check. Alpha 30 degree means what? Same as uncontrolled. No, no. Alpha 30 degree, if it is same as the uncontrolled, then alpha 0 degree means alpha 0 means same as uncontrolled. Na? Alpha 30 degree I have asked. I0 becomes 0 for some time. Okay. Okay. Alpha 30 degree means what? Please listen. Alpha 30 degree. This is like alpha less than 30 degree. Na? Alpha 30 degree means we are supposed to apply gate pulse to thyristor T1 where? We are supposed to apply the gate pulse to thyristor T1 at this instant. Na? Yes or no? We are supposed to apply gate pulse to thyristor T2 at pi. Na? We are supposed to apply gate pulse to thyristor T3 at 5 pi by 3. You can measure. Na? Pi by 6 plus 30 degree means what? It is a pi by 3. 5 pi by 6 plus 30 degree means pi radian. 9 pi by 6 plus 30 degree means 5 pi by 3. So what will happen at this instant? I am turning on. At this instant, I am applying the gate pulse to thyristor T1. So before T1, which thyristor will be in a conduction mode? T3. When T3 is in a conduction mode, output voltage will be VCN. So you can check output voltage will be same as that of the VCN. It reaches the 0 value. And from that instant, it will suddenly increase to the VAN. Are you getting the point? Means if alpha is 30 degree means here we are having the decrease and from non-zero value to the sudden increase. Na? But if alpha is 30 degree, then it will be like from this point, it will be decreasing, reaches the 0 value. And again, at the same point, it will be increasing to the VAN value. Right? Means it reaches the 0 value and again increases, reaches the 0 value and again increases. That is for alpha equal to 30 degree. Okay. For alpha greater than 30 degree, we'll discuss tomorrow. Okay. But for alpha 30 degree, please try to understand alpha 30 degree. Okay. This is very important. For alpha 30 degree, I will only draw the waveform of V0 and I0. Then we'll stop here. Okay. So for alpha 30 degree means this is like your, yes, this is like your alpha equal to 0 na for thyristor T1. This point is like alpha equal to 0 degree for thyristor T2. This point is like alpha equal to 0 degree for thyristor T3. Okay. Now you can check if this is alpha 0 degree na pi by 6. Omega T pi by 6 means alpha 0. So if we want to keep alpha 30 degree means what? I need to add 30 degree into this pi by 6 na. So that will be your this point na. So this point is like pi by 3 na. This point is like a pi by 3. Means we are supposed to apply the gate pulse to thyristor T1 at pi by 3. Pi by 5 pi by 6 is nothing but alpha equal to 0 for T2. Means if I apply the gate pulse to thyristor T2 at 5 pi by 6, omega t 5 pi by 6, the meaning is we are keeping alpha equal to 0 degree. If we are interested in keeping alpha 30 degree, means we are supposed to apply the gate pulse to thyristor T2 at this instant. This instant is nothing but 5 pi by 6 plus 30 degree, na? So that is the pi radian. 9 pi by 6 plus 30 means this instant is like your 10 pi by 6, means 5 pi by 3. 5 pi by 3. Yes or no? So here you can check, this instant is nothing but where we are supposed to apply the gate pulse, that is for alpha 30 degree we are keeping, na? Right? So you can check, I'm applying gate pulse to thyristor T1 here, thyristor T2 here, thyristor T3 here. So this point indicates your alpha. This point indicates alpha. This point indicates alpha. Okay. So now you can check, at this instant we are firing thyristor T1. Before this, which thyristor was in a conduction mode? T3, continuous conduction. That is a T3. Okay. T3 is in a conduction mode, means in the output we will be getting VCN. VCN in the output means it will be like this. It will be reaching the 0 value. You can check at this instant pi by 3, VCN is 0. So as soon as your output voltage reaches 0 value, but at the same instant we are firing the thyristor T1, na? So suddenly when T1 turns on, your output voltage will suddenly jump to the VAN value. Okay. So in the output will be getting this type of wave shape, suddenly increase to the VAN. And again it will be like this VAN, this type of waveform will be getting. Okay, VAN. It will reaching the 0 value at pi. At the same instant we are firing thyristor T2, na? So when T2 is fired, in the output will be getting, yes, when T2 is fired, in the output will be getting VBN. So suddenly increase to the VBN, and again the same will be followed till this instant. You can check VBN reaches 0 at this point, 5 pi by 3, and at this instant we are firing T3. So when T3 is fired, in the output we will be getting the VCN. This is for alpha equal to 30 degree. Please try to understand. Okay. So if this is the V0, what about the I0? I0 will be in phase with V0 now. The meaning is, what is happening here? Just a minute here, 13 pi by 6. Na? This will not reach the 0 till 13 pi by 6, because remaining portion is here we are having, right? So it will be like this. It will be like this. Okay. Some part here and remaining part is here, right? VCN. So this is a VAN, this is a VBN, and here it is a VCN, right? So if you compare this waveform and this waveform, what is the difference? If alpha is less than 30 degree, your output voltage is not reaching the 0 value. But whereas if alpha equal to 30 degree, it is reaching the 0 value. And from the same point, yes, from the same point, it is jumping to the, yes, again, non-zero value. Yes or no, right? This is the alpha 30 degree. Please try to understand. Alpha 0 degree means it is like your diode rectifier waveform. So you can check alpha 0 degree means this type of waveform we will getting. It is decreasing and from the same point it is increasing, na? Decreases and from same point increases, decreases and from same point increases. So smooth decrease, smooth increase, smooth decrease, smooth increase. If you check, if alpha is less than 30 degree, yes, there is a sudden increase, there is a sudden increase. Alpha equal to 30 degree, it is touches the 0 value, reaches the 0 value, and again increases, reaches 0 value, again increases. So if alpha greater than 30 degree, then what will happen? Then there will be the discontinuous conduction. Okay, we'll discuss it tomorrow, right? We'll discuss it tomorrow. Okay, okay. So stop here. Some derivations are there. We'll derive these derivations tomorrow. Okay, right. Yes. Few questions I will be taking today. Okay, and remaining doubts I will continue tomorrow. Right? Yes, please.
Yes, sir.
Just for 20 minutes, I am having 20 minutes because I need to go. Right?
Okay.
Tomorrow we'll continue. Yes, please.
Okay, sir. So my doubt is in the same waveform from pi by 6 to pi by 3, the VCN voltage is actually less than VAN, right?
Yes.
So wouldn't that thyristor turn off at that time? Like how can VC come in between that point? We get the output at that time, no V0. But if the
From
thyristor
pi
turn,
by 6 to pi by 3, you are saying.
yes, sir.
From pi by 6 to pi by 3, or before that, before pi by 6, which thyristor was in a conduction mode?
T3 was in
T3.
conduction.
Suppose T3 is in a conduction mode.
Yes, sir.
When T3 is in a conduction mode, current was flowing like this, na? VCN, T3, load, and again back to the VCN.
Yes, sir.
The
Yeah.
output we were getting the VCN.
Yes.
Now, even though you can check, even though at pi by 6 it is, after pi by 6 it is VCN is less than VAN.
Yes, sir.
But you can check at the cathode of thyristor T3, VAN will appear only when thyristor T1 is in a conduction mode, na?
Yes, sir. Correct. Yeah.
So if the thyristor T1 yet we have not applied the gate signal,
Oh, that
whether our
voltage
thyristor
wouldn't
T3
appear.
will- whether
in-
our thyristor will be in a reverse bias, no, na?
No. That voltage wouldn't appear.
Right?
Correct, sir. Okay, sir. Got it. Thank you, sir.
Okay.
Good evening, sir.
Good evening.
Sir, I just want a clarification in the AC and DC power value, sir.
AC and
DC. I will tell you, sir. P not average is equal to V not average, I not average for DC, no?
please repeat.
P average equal to V not average into I not average for DC.
No. P0 average is equal to V0 average into I0 average, you are saying, na?
Yes, sir, for constant DC.
No, actually it depends. If I0 is constant, then that will be true.
Okay, sir.
If
Sir, when we
load
take-
current is constant, na, if the load current is constant, then this expression will hold. But suppose if you are having a load is a resistive load, then we
Okay.
cannot use this expression.
Then which we can use, sir? It's confusing that. Could you write that, sir? I will
Yes,
copy that.
I will just a minute. Let me write here. Yes. Suppose if load is R load, na,
Yes, sir.
then your P0 average is equal to V0 RMS into I0 RMS. Because the thing is your V0 as well as I0 waveform are not constant. Yes or no?
Yes, sir.
R load, V0 and I0 both are varying, na? So that's why we cannot use that expression here. So it is a P0 average. Suppose if load is REL and highly inductive, okay? Then how to find highly inductive means your I0 is constant, okay?
Okay, sir.
Then in that case, you can write P0 average is equal to V0 average into your I0 average. And that I0 average is nothing but capital I0, no?
Yes, sir.
So this is the expression for REL load, highly inductive. Suppose if load is RE load, okay? If load is RE load, then P0 average is equal to I0 RMS square into R plus E into I0 average. So please try to understand the thing. What the P0 average indicates, it is a average value of V0 and I0 product.
Yes, sir. Same as diode
Now,
previous.
yes. Now in this case, if you check here, yes, this is the same as that of the diode. Na? E is constant. Na? If anyone is constant, na? E, in this case, it is a E is constant RE load. If E
Yes.
is constant, then the power consumed by the average power of the E is nothing but that constant value into I0 average.
Yes,
In
sir.
this case, it is like a I0 is constant. Na? In this case, it is like I0 is constant.
Yes, sir.
So that's why this average is V0 average into I0. If
Okay.
out of the two, if V0 and I0, out of the two, if any one is constant, then your P0 average is like that V0 average into I0 average. If both
Oh.
are varying, then it's like V0 RMS into I0 RMS. Is this clear?
Okay. Yes, sir. Sir, one more, sir. When we take cos angle in that, sir, mean power inputs
Where?
are that one. VRMS into IRMS into cos of angle between VS into IS.
No. Right? We need not to take that.
When we take that, sir.
into I0 RMS into cos means you are saying that just like your AC VI cos phi.
Yes, sir.
No, but here it is our DC now. Output is DC.
That's for
And how
input.
we have derived this expression na R load. You can
Yes,
recall
sir.
here single phase half wave controlled rectifier or uncontrolled rectifier. For resistive load, we have derived the expression of P0 average, right?
Yes, yes, sir. Yes, sir.
Please go through that. Also, in a first chapter that piecewise modeling na, at that time
Yes, sir.
you derived these expressions, right?
Okay, sir. I will check, sir.
Okay, please.
Thank you so
Hello,
much,
sir.
sir.
Okay.
Hello, sir.
Yes, please.
Sir, 6F, sir, 6F.
6F.
Sir, before one, sir, that one, he have taken that cos phi, no, sir, and cos alpha by 2.
Where?
Sir, here,
Here.
on, sir, active power input.
Yes.
Sir, when to use that formula, sir, cos alpha is equal to, we have written one formula for cos square, no, sir.
Cos square wave.
Yes, sir, yesterday.
Fourier series you are saying.
Yes, sir, yes, sir.
Okay,
have
okay.
input
Then
power
which
factor.
formula you are saying? Which formula?
Sir, 2 root to cos alpha by 2 by root or pi into pi minus alpha into cos alpha by 2.
Yes. 2 root 2 means this one, na?
Not this one, sir. Sir, by root or pi into pi minus alpha is best.
Read once what that formula or expression is.
Sir, 2 root to cos alpha by 2 by root or pi into pi minus alpha into cos alpha by 2.
And to left hand side, what we have written?
Sir, input power factor, sir.
Okay, that is the input power factor expression actually.
Yes, sir.
And here we are finding the real power, active power.
Yes, sir. That means that is input only, no, sir. Active power from.
No, but the thing is, yes, you can use the input power factor here also. Just like your VS1 RMS, okay, into your IS RMS, into that input power factor.
Okay, that one also can use. Or this value is equal to cos alpha by 2 will get, sir.
Yes. But most accurate will be, that will be giving you the near answer. But the most accurate will be this one, because you can check here what here we are doing. Fundamental component of the source RMS value.
Yes, sir.
Anyway, source is your pure sinusoidal, na?
Yes, sir.
We are taking the fundamental component of the source current.
Yes, sir.
And into cosine of the angle between the two. Actually, the thing is,
yes, sir.
Whatever the formula we are having, that input power factor, okay,
Yes, sir.
that can be used when your either voltage or current waveform is a sinusoidal and second one is a non-sinusoidal.
Okay, sir.
Right. So now in that case, if they ask directly the input power factor, then directly you can use that expression, that formula. Okay.
Okay,
If
sir.
they ask for the active power input, you can use
Yes,
either
sir.
this one or that
Yes,
one
sir.
also.
Sir,
Right?
if we are,
Be careful.
Yes, sir.
This will give you the more accurate result, because here we are
Okay, sir.
considering the IS1 RMS, na?
Yes, sir.
And in that expression, generally we consider IS RMS.
Sir, when we use that expression, we have to write IS RMS.
Yeah. Then if you take the IS RMS, na, then it will be like your that thing,
harmonic component plus fundamental.
Yes, that is the problem. But here actually most of the your share, okay, because in the source we are having only fundamental, na.
Yes, sir.
So if I want the active power, if my source is not having the third harmonic component, so what
Yes,
about
sir.
the active power output of the third harmonic component? It will be zero.
It will be 0, sir. Yes, sir.
That's why we are taking only fundamental.
Okay, sir. Okay, sir.
Are you getting the point?
Yes, sir. I'm good. Yes, sir. Thank you, sir.
Yes. Okay. Yes, next. Hello.
Hello, sir.
Yes, please, Avinash.
Sir, one problem you have taken, that is quadratic equation is found in that, sir.
Just a minute. Yes, that I0 something, na?
Yes, sir. I0 problem. Actually.
Just a minute, just a minute. Yes, here it is.
Sir, you are told, sir, here I0 we get sir 2 values. Then which value I have to take, sir? Actually,
Lower value, lower value.
sir, why, sir? Means, is there any?
Because if you check, if I use the higher value, na,
Yes, sir.
please put here higher value of I0 and try to find the mu value.
Yes, sir.
What value of, if suppose if you use that I0 was something 637 something, na, kuch to.
Yes, sir. Yes, sir.
If you put here 637 point something that and check the value of mu, you will be getting very high mu here.
Okay, okay, sir.
Whether your overlap angle will be high, not possible, na?
Yes, sir.
So that's why you need to take the lesser value, right?
Yes, sir. Sir, this overlap angle, sir, depends on which parameters, sir, actually.
It depends on LS actually.
It's inductor value.
Hi, that source inductance.
Okay, okay, sir.
And the second thing is your supply frequency.
Okay, okay, sir. Sir, source inductance increases, sir, then mu will increase or decrease, sir? Actually.
Mu will increase.
Increase as per inductance.
Yes, yes, yes. Because inductor is the element which opposes the change in the current, na?
Yes, sir. Yes.
So your slope of IS will be, that is changing from minus I0 to plus I0, na? If LS is more, so your slope will be lesser.
Okay,
Means
okay.
that will be like inclined like shape, okay?
Yes,
So
sir.
more mu will be getting, right?
Yes, sir. And sir, in one more topic in yesterday's lecture, sir.
Okay.
Sir, we have used the Fourier analysis. Actually.
Yes, tell me, tell me.
Sir, is there any alternate method, sir, instead of Fourier analysis to solve that expressions?
No, no, no. We have only Fourier analysis, Fourier tool.
And sir, why we have used, sir, that means only Fourier analysis?
Because the thing is, if you check resistive load and a REL load, in a
Yes.
resistive load, it is like we are having a voltage and current, both are sinusoidal,
Yes, sir.
supply. But whereas if you check in the REL load, voltage is sinusoidal, but current is non-sinusoidal, na? It is a square wave or quasi square wave.
Yes, sir.
So in that case, we cannot find the input power factor directly by equating input power is equal to output power. So for that, what we are doing, we are with the help of Fourier series, whatever our load current waveform is there, na, that's sorry, source current waveform,
Yes.
non-sinusoidal. That waveform we are dividing into a various sinusoidal components, just like a fundamental, third harmonic, fifth harmonic, etc.
Yes.
Okay. And from that, actually, we are picking the fundamental only. And we are comparing the fundamental source voltage and fundamental source current. And with the help of that, we are finding the input power factor.
Okay, okay, sir.
Right? So we don't have alternate tool. We need to use only Fourier because we are having only Fourier series tool that will divide your non-sinusoidal periodic signal into the sinusoidal signals.
Yes.
Right?
Sir, but sir, by using fundamental components and we have find the power factor such
By using fundamental
components, sir, we have find the power factor of input side.
Yes, yes.
So, sir, what about that third harmonic or means the harmonic components, sir?
Actually, the thing is, you are having the source is a pure sinusoidal source voltage.
Yes, sir. Yes, pure
So
sir.
if source voltage is pure sinusoidal,
Yes.
then definitely your overall power factor of the converter or the input side is nothing but your only fundamental power factor. But if source is also having the third harmonic component like thing,
Yes.
okay, means source voltage is also non-sinusoidal, source current is also non-sinusoidal. Then
Yes.
in that case, yesterday we discussed one numerical. At the last, there was some note was there, right?
Okay.
So like that, we need to find the input power factor. Okay.
Means, sir, we can
one more
consider.
thing- one more thing, even though the third harmonic, fifth harmonics are present there, okay,
Yes.
but the most of the share of the source current is
Yes.
of fundamental only, na?
Yes, sir. Yes.
Almost 90% is the fundamental. Remaining 10% we are having harmonics, right?
So, sir, for that we have considered the fundamental waveform for finding input power factor.
Yes, yes, only fundamental for finding the input power factor. Okay.
Okay, sir. And sir, in a three-phase rectifiers, we have done, sir, the transformer primary side delta or star connected.
Yes, it primary it might be delta or star, but secondary should be star
Secondary should be star. Okay.
because we require a 4-wire, na?
Yes, sir. Yes, sir.
So that's why it should be connected in star, right?
Yes, sir. Yes, sir.
Okay. Okay.
Thank you, sir.
Okay. Yes. Yes, come on, please. Last 5 minutes, sir, please.
Hello, sir.
Yes, please.
Sir, in the last topic you discussed, three-phase three-pulse control rectifier, sir.
Yes, 3-phase 3-pulse rectifier. Control, na?
Yes, sir.
Yes, in that.
Alpha equal to 0, we are taking omega t equal to pi by 6 now, sir.
Correct.
When alpha equal to 30 degrees, what is the value of omega t?
Pi by 3.
When alpha equal to pi by 3, omega t is also pi by 3, sir.
When alpha is 30 degree, you are saying, na?
Okay, sir. I understood.
Alpha 30 means pi by 6.
Yes, sir.
Omega t is pi by 3, right?
Okay, sir.
Yes, after this, I need to add na angle.
Understood.
Correct. Okay. Okay.
Hello, sir.
Yes, please.
Sir, in the source inductance waveform, sir.
Source inductance.
Sir.
Okay. Source effect. Source inductance effect. Okay.
Sir.
Yes, in this.
Sir, in this actually I did not get why when it is sir. This, sir, in this I not get why when it is increasing or decreasing from this I0 to minus I0 or like that. Why is it like increasing or decreasing as straight line itself and not like any other curve or like that, sir?
Okay. You can check here.
Yes.
We have drawn this type of circuit equivalently here, right? In this circuit, we are having equivalent.
Sir.
During this interval, na, alpha to pi, alpha plus mu.
Sir.
We are having only source and we are having an inductor, na?
Sir.
Right? So it is like your Vs is equal to Ls into dis by dt. Okay? So your di by dt is nothing but what? Vs into sine of omega t by Ls. Okay? So strictly speaking, your this change, okay, your this change will be, it is not like a linear, okay, it will be like somewhat sinusoidal type thing. But whether this angle is very large,
No.
this angle is very small, na? So you can check for small values, what is the sine theta?
Small.
It is like a linear, na? You can check sine 0 is 0, na? You can check sine of 0.5, you can check. You can check a sine of 1, right? From that you will understand if angle theta is a small, na, definitely your sine theta will be like a linear.
Okay, sir.
Simply you check the angle like a sine of 0.5. Check for sine of 1. Check for sine of 1.5. You will be getting nearly the same difference, okay, of sine values between theta 0 to 0.5, 0.5 to 1, 1 to 1.5. Okay, so that's why it is nearly sinus. It is like a linear, nearly linear, right?
Okay, sir.
But if angle mu is high, na, then in that case you will observe like a sinusoidal, right?
Okay, sir.
Right.
So this mu will be generally in what range, sir? Like
mu range is hardly 5 degree, okay, 5 to 7 degree.
Okay, sir.
Because value of LS is comparatively very less, na?
Hi, sir.
Okay.
Okay, sir. Thank you, sir.
Okay, okay. Yes.
Hello, sir.
Yes, please.
In the three-phase three-pulse rectifier,
Three pulse, na?
yes, sir.
Yes.
Sir, I just
Ah,
wanted to ask one thing. If one of the diodes is in opposite direction, then
one of the diode is connected in opposite direction.
that means if suppose D2 is in opposite direction, so when the next gate pulse we are going to apply, then it will follow
Diode or
the
resistor?
diode.
No, you are saying diode and you are saying the word get pulse.
Sorry. Thyristors. In the three-phase half-wave controlled rectifier, the last one you
Controlled
discussed.
rectifier, and if one of the thyristor is connected in opposite right direction.
Yes, sir. Suppose T2 is connected in
Suppose T2
opposite
is
direction.
connected in- Okay.
So when the second gate pulse is applied, so it will follow the VAN waveform only, no? Till
Second get pulse means
at 5 pi by 6. At 5
at 5 pi by 6 you are saying. Okay.
Yes, sir. So it will
Means,
follow.
you are saying that we are connecting this T2 in a reverse direction. Okay.
Reverse direction.
It is like a cathode here, anode means like this.
Anode. So it will be in
Like
reverse
this, na?
in reverse mode when we apply
Okay.
it. 5 pi by
Here
6.
voltage is the VBN. Here voltage is VAN. Huh? Now your
VAN.
question is
When we apply gate pulse at 5 pi by 6,
okay.
then the waveform will follow VAN only. No, VBN will not be followed because it is.
Yes. VBN will be your lesson, na here. And
Yes, sir.
VAN will be more. But the thing is, if you connect it like this, na, the voltage across thyristor is minus plus, that is a VT2. This VT2 is equal to your VAN minus. Okay.
Okay. Sir.
Okay. So it is a VAN minus VBN, correct?
Yes,
So now
sir.
if you check here, now you are applying the gate pulse, you are saying that at 5 pi by 6.
Yes, sir.
Then your thyristor will not turn on,
Yes, sir.
right? Because it is connected in reverse, na? But my question is, before that, it is
Yes.
VAN minus VBN, na?
Yes,
So you
sir.
can check VAN is greater here and VBN is less here. During this interval, VAN is greater, na?
Yes, sir.
So this thyristor, no, VAN minus VBN, yes.
So T1 will be
Then-
on.
No. The thing is like compared to your VAN value,
Yes, sir.
is VAN minus VBN, na?
Yes, sir.
Because when you connect this in a reverse direction, na, it is VAN minus VBN means this voltage will appear across thyristor T2.
Yes,
So you
sir.
can check VAN means only this voltage. If you take the difference VAN minus VBN, this difference will be greater than that of whatever your voltage, na, phase voltage.
Okay.
Then that thyristor T2 will be more positive. But if you don't apply, right, the gate pulse to thyristor T2 till 5 pi by 6, then no problem. But if you apply the gate pulse before 5 pi by 6, then there will be means thyristor T2 will conduct somewhere. Okay. But if you don't apply the gate pulse, then definitely after this instant also, means after applying the gate pulse also, your VAN will be in the continue. We will be getting the output voltage will be VAN only.
If we apply the gate pulse, then what happens, sir? Can you repeat?
If we apply the gate pulse, where you are saying?
At 5 pi by 6, what is happening?
At 5 pi by 6.
Yes, sir.
Okay. And before that, before that, thyristor T1 is in a conduction mode.
T1, yes, sir. T1 is in conduction.
T1 is conduction mode, and before 5 pi by 6, if we apply the gate pulse, okay, then here voltage is like VAN, na? T1 conduction
Yes,
mode means definitely here it is a VAN.
Yes, sir.
Okay.
So
Here it is VAN, here it is VBN, na?
VAN is at higher potential.
Yes, VAN will be more positive.
Positive.
Here it
Yes.
is, na? Compared to that of the VPN. So if you apply gate pulse before, then your thyristor T1 will committed earlier.
Okay.
Right? Means it depends to when you are applying the gate pulse to thyristor T2, right?
Okay. Okay. Thank you.
That will change. Okay.
Okay.
Yes. Yes. Anil Kumar.
Good afternoon, sir. Good evening, sir.
Good evening. Please fast, a bit fast.
Okay, sir. In 39 slide.
13.
9, sir.
39. Just a minute.
Sir, in this, I didn't get that magnitude, sir. I naught by n.
This I naught by n. Okay, okay. This magnitude.
Yes, sir. I naught by n.
Is you can check this diagram. Okay.
Yes, sir.
When the secondary winding current is I0, na?
Yes, sir. Secondary winding current is
This
I0.
current is I0. Then what about the primary winding current? It is a n/1:1, na? Means it is like a step down for a voltage.
Okay, sir. Okay.
So it is like a current step up, na?
Yes, sir.
Means from here to here current will step up. Primary to secondary current will step up. Means primary
Sir.
current will be lesser than that of the secondary current.
Okay, sir.
That's why it will be I0 by n, right?
I0 by n, yes, sir.
Clear?
Yes, sir. Clear, sir.
Yes.
Sir, another problem, sir. Three-phase, three-pulse controlled rectifier.
Three-phase,
Three-phase, three-pulse uncontrolled rectifier, sir.
uncontrolled you are saying. Okay.
Yes, sir. Sir, in this, how we can find that PIV rating, sir? I didn't get that.
How we can find?
PIV rating, sir, of each diode, sir, before
PIV
slide.
rating. Okay. Just a minute. Let me tell you. Yes, suppose this is as I
Yes, sir.
said, in the operation at a time, one diode will be in a conduction mode, na?
Yes, sir, one diode.
Suppose diode D1 is in a conduction mode.
Yes, sir.
So when D1 is in a conduction mode, what about the voltage here? It is a VAN, na?
Yes, sir.
So if it is VAN, here it is VAN, here it is VAN, na?
Yes, sir, VAN.
Now you can check when D1 is in a conduction mode, remaining two will be in off state, na?
Yes, sir, off state.
D2, D3 will be in off state. So at the
Yes, sir.
cathode of diode D2, the voltage is VAN.
Yes, sir.
At the anode of diode D2, the voltage is VBN, na?
Yes, sir, VBN.
What is the voltage across diode D2? VBN minus VCN.
Plus VAN. Yes, sir.
VBN minus VAN.
Line voltage.
VBN minus VN is line voltage.
Line voltage. Yes, sir.
Okay. Right. Okay. ठीक है.
Thank you, sir.
Yes, we'll stop here. Tomorrow we'll be meeting at morning 6:30. Okay. Probably I will be taking the session from 6:30 to 9 only. Okay. After 9 I am having one important task, right? And after that again tomorrow evening 5 to 9 we'll be meeting. Probably tomorrow we'll finish the rectifier, and day after tomorrow we'll be starting the DC to DC converter, right? Okay. Thank you. Thanks to all of you.